There are places on Earth where time doesn't behave the way it should, where minutes feel like centuries and millions of years collapse into a single moment of wonder, where you can touch rocks that remember when the continents were young, or watch light that has been travelling through darkness since before humans existed. This is a journey to 20 of the strangest places our planet has hidden away. Not the famous landmarks that fill postcards, but the secret corners where nature has been conducting experiments so bold, so impossible, that they challenge everything we think we know about how the world works. Rotorua Geothermal Fields, New Zealand. Steam rises from 1,000 vents across the landscape today, creating a scene that belongs more to Earth's primordial past than to its settled present. From the wooden walkways that wind through to Puia, you can hear the sound of the planet's interior processes made audible. The deep rumbling of underground chambers, the sharp hiss of steam escaping through cracks in the earth, the gentle bubbling of mud pools that have been cooking themselves for centuries. The air carries the unmistakable scent of hydrogen sulfide, the rotten egg smell that tourists learn to accept as the signature of active geothermal fields, mixed with the mineral richness of water that has travelled through deep rock and emerged transformed. The famous Pahutu geyser erupts as you watch, sending a column of superheated water 30 metres into the air with the regularity of clockwork, though its schedule is determined not by human engineering but by the complex interplay of underground pressure, temperature and water supply that has been operating here for thousands of years. Around it, smaller geysers and hot springs create a landscape that seems to breathe with its own rhythm, expanding and contracting as pressure builds and releases in chambers carved from rock by centuries of circulating hot water. This is Rotorua today, a city built literally on top of one of the world's most active geothermal systems, where hotel swimming pools are fed by natural hot springs and the local power plant draws its energy directly from steam that rises from the earth. Tourists come from around the world to experience this intersection of natural wonder and human adaptation, to soak in thermal pools and walk through landscapes where the distinction between geology and biology, between earth and atmosphere, becomes meaningless. Step back just over a century, to the morning of June 10th, 1886, when the sound of distant thunder rolled across this landscape even though no clouds darkened the sky. Local Maori communities, who had lived with these geothermal features for over 700 years, recognised immediately that something unprecedented was happening. The thunder was not coming from above, but from within the earth itself, from Mount Tarawera, the sleeping volcano that dominated the horizon to the southeast of Lake Rotorua. When Tarawera erupted that night, it transformed the entire geothermal landscape in a matter of hours. The explosion was heard over 600 miles away in Auckland, and the ash clouds darkened the sky for days across the North Island. Most dramatically, the eruption completely destroyed the pink and white terraces, silica formations that had been called the eighth wonder of the world, replacing them with an entirely new geothermal system called Waimangu, which became the world's youngest geothermal field. The Maori communities that lived here before the eruption had developed sophisticated understandings of how to work with the geothermal landscape. They used natural hot pools for cooking, bathing and healing, and had learned to read the subtle changes in steam patterns and water temperatures that could signal shifts in underground activity. The village of Te Wairoa, destroyed in the 1886 eruption, had been a thriving community that hosted tourists who came to see the famous terraces, creating one of New Zealand's first tourism industries based entirely on geothermal wonders. But step back further to the years before European contact, when the thermal fields of Rotorua supported a complex Maori civilization that had learned to live within and alongside geological forces that could reshape the landscape overnight. Archaeological evidence shows that Maori settlement here began around 1350 CE, when Polynesian navigators first arrived in New Zealand and discovered a landscape unlike anywhere else in the Pacific. The thermal features that surrounded Lake Rotorua provided year-round sources of hot water in a climate that could be harsh during winter months. Maori communities developed techniques for using natural hot springs to preserve food, cook meals, and maintain comfortable temperatures in their settlements. They called the area Te Rotorua Nui a Kahumatamomoe, the Great Crater Lake of Kahumatamomoe, recognizing that they were living within the remnants of ancient volcanic processes. Step back 1800 years to around 232 CE, when the landscape that would become Rotorua experienced one of the most powerful volcanic eruptions in recorded human history. The Taupo eruption, centered on Lake Taupo just 60 kilometers south of present-day Rotorua, ejected more than 120 cubic kilometers of material into the atmosphere, creating pyroclastic flows that traveled hundreds of kilometers in ash clouds that may have affected global climate patterns. This eruption fundamentally reshaped the geothermal systems throughout the region. The massive release of energy and material created new underground fracture systems and altered the flow of groundwater through the rock layers that feed the thermal features. Many of the hot springs and geysers that exist in Rotorua today can trace their origins to changes in underground hydrology caused by this catastrophic event nearly 2 millennia ago. The Taupo eruption was powerful enough to be recorded in Chinese and Roman historical records as unusual atmospheric phenomena, but locally it represented a complete reset of the landscape. Everything that existed here before 232 CE was buried under meters of volcanic debris, creating the foundation upon which all subsequent ecosystems and human settlements would develop. Step back 26,000 years to the last major ice age, when sea levels were lower and New Zealand's climate was significantly colder and drier. The geothermal activity that characterises modern Rotorua was already well established, but it operated in a very different environmental context. The thermal features provided refugia where plants and animals could survive during the harshest periods of glacial climate, creating biological oases in landscapes that were otherwise too cold to support diverse ecosystems. Step back 2 million years to the beginning of the geological processes that created the Taupo volcanic zone, the 350-kilometre-long belt of active volcanism that extends from White Island in the Bay of Plenty to Mount Ruapehu in the central North Island. This volcanic zone exists because New Zealand sits at the boundary between two major tectonic plates, the Pacific Plate and the Australian Plate. The collision and subduction of these plates creates the geological processes that drive all volcanic and geothermal activity throughout the region. As the Pacific Plate slides beneath the Australian Plate, it carries water-saturated ocean floor sediments down into the Earth's mantle, where they partially melt and create magma that rises back toward the surface. This magma doesn't always erupt directly, but its presence in underground chambers heats the groundwater that feeds the geothermal systems. The specific geology of the Rotorua area makes it particularly suitable for sustained geothermal activity. The bedrock consists largely of volcanic rocks deposited during millions of years of previous eruptions, creating a complex three-dimensional network of fractures, porous layers, and underground chambers that allows water to circulate deep enough to be heated by contact with hot rock or magma. Modern research using seismic imaging and geochemical analysis has revealed that the geothermal systems around Rotorua are fed by water that has been underground for decades or centuries, slowly circulating through rock formations at depths of several kilometers where temperatures can exceed 300 degrees Celsius. This water gradually rises back toward the surface through the network of fractures and cavities, cooling and mixing with shallower groundwater to create the diverse range of temperatures and chemical compositions found in different thermal features. The geothermal fields also demonstrate how different timescales of geological and biological processes interact to create complex ecosystems. Thermophilic bacteria and archaea that can survive in the hottest water create biological communities that are among the most ancient on Earth, while the silica deposits created by the hot springs provide substrates for more conventional plants and animals adapted to the warm, mineral-rich environment. 20 places, 20 windows into the impossible, from caves sealed away since the dawn of complex life, to geysers that mark time with their faithful eruptions, from lakes that glow pink with ancient bacteria to pillars of stone that float in morning mist like forgotten dreams. These places remind us that we are part of something much larger and more mysterious than our brief human lives. They show us that wonder isn't just an emotion, but a way of seeing, a way of recognizing that we live on a planet where the impossible happens every day, usually too slowly for us to notice. But now you know where to look. Mammoth Cave System, Kentucky. The headlamp beam cuts through absolute darkness, revealing limestone walls that seem to breathe with moisture. You're standing 280 feet below the surface of Kentucky, inside what scientists call the world's longest known cave system. Above your head, roots from oak trees stretch down through tiny cracks, still searching for water that began this journey when your great-grandmother was learning to walk. The air here moves differently, carrying scents of minerals that have been dissolving since before humans learned to make fire. This is Mammoth Cave, where over 426 miles of mapped passages wind through the earth like a vast underground circulatory system. But that number grows every year. Just last month, the Cave Research Foundation added another half-mile to the official count. Somewhere in the darkness beyond your light, water is still carving new tunnels, following paths it started millions of years ago. Your footsteps echo off walls that hold secrets spanning 350 million years. The limestone beneath your boots formed when Kentucky lay underwater, covered by a warm, shallow sea that stretched from here to what would someday become the Rocky Mountains. Tiny marine creatures lived and died in that ancient ocean, their shells and skeletons settling layer by layer on the seafloor. For 70 million years, this process continued, building the bedrock that would eventually become the foundation for one of Earth's most extraordinary underground worlds. The water you hear trickling in the distance carries a story that began when those seas retreated. About 325 million years ago, the climate shifted, and Kentucky emerged from the depths. Sandstone and shale covered the limestone like a protective blanket. But water always finds a way. Rainwater, made slightly acidic by carbon dioxide in the atmosphere, began seeping through the upper rock layers. When it reached the limestone below, a chemical reaction started that continues to this very moment. Every drop of water entering this system becomes a tiny sculptor. The limestone, composed primarily of calcium carbonate, dissolves in the acidic water, creating a solution that flows toward the lowest point it can find. That lowest point then and now is the Green River, which cuts through this landscape like a master drain. The water follows the path of least resistance, exploiting tiny fractures in the rock, widening them grain by grain, year by year, century by century. But the cave you're walking through didn't form overnight. The upper levels of Mammoth Cave that tourists visit today were fully developed by 3.2 million years ago. Scientists know this because they've found and dated quartz pebbles embedded in the cave walls, carried here by ancient streams when the Green River flowed 200 feet higher than it does today. These pebbles are like timestamps, marking moments when the underground rivers carved their channels at specific elevations. As the Green River cut deeper into the landscape over millions of years, the cave's water table dropped with it. New passages formed at lower levels while older tunnels higher up were abandoned by the flowing water. This created the multi-story cave system explorers navigate today. The dry upper passages, like the one you're standing in, represent ancient river channels. The active lower levels, where the river Styx and Echo River still flow, show where the water works today. The temperature here never changes. It holds steady at 54 degrees Fahrenheit year-round, the average annual temperature of the surface world above. This constancy exists because you're insulated by hundreds of feet of rock from the daily and seasonal temperature swings that define life on the surface. Time moves differently here, measured not in hours or days, but in the slow rhythm of geological processes. In 1838, a teenager named Stephen Bishop arrived at this cave as an enslaved guide. He possessed an extraordinary gift for spatial memory and spent 19 years mapping these passages by lamplight, creating detailed charts that remained the most accurate representation of the cave system for decades. Bishop discovered and named many of the cave's most famous features, including the River Styx, which he named after the mythological river separating the world of the living from the underworld. He understood intuitively what modern geologists have proven with instruments. These passages follow patterns of weakness in the rock that were established millions of years before humans existed. The River Styx that Bishop named still flows 360 feet below the surface. When cave researchers take boats along its dark waters today, they're travelling routes carved when ice sheets covered much of North America. The river's temperature varies by mere fractions of a degree throughout the year, creating an environment so stable that unique species have evolved here. Blind cavefish navigate waters that have flowed in darkness for millions of years, their lateral line systems detecting pressure changes in water that moves according to rhythms established long before their ancestors lost their eyes. Modern exploration of Mammoth Cave began in earnest in 1957 when the Cave Research Foundation started systematic mapping and survey work. Using techniques Stephen Bishop could never have imagined, researchers have revealed connections between cave systems that, early explorers thought were separate. In 1972, cavers discovered the connection between Mammoth Cave and the nearby Flint Ridge cave system, instantly adding 10 miles to the known length. These connections continue to be found, each one revealing that the underground landscape is even more interconnected than previous generations realized. The water that drips from the ceiling above your head began its journey on the surface perhaps decades ago, percolating slowly through soil and rock. Some drops follow fast routes through large cracks and arrive in the cave within hours of a surface rainstorm. Others take the slow path, filtering through tiny pores in the limestone, arriving decades or even centuries after they first soaked into the ground. This means the water pooling at your feet represents rainfall from many different time periods, mixed together in underground pools that know nothing of the seasons passing overhead. Deep below where you stand, at the very bottom of the cave system, water continues the work it began 350 million years ago. The lowest accessible parts of Mammoth Cave flood regularly when the Green River rises, connecting the underground world directly to the surface hydrological cycle. During these floods, sediment and nutrients from the outside world wash into the cave, feeding ecosystems that have evolved in perpetual darkness. Cave researchers working at these lowest levels sometimes encounter currents strong enough to make exploration dangerous, reminders that the forces shaping this place operate on their own timeline, indifferent to human schedules. The water that carved the passage you're walking through didn't hurry. It worked grain by grain, following chemical and physical laws that haven't changed since the cave began forming. The same process continues today, carving new passages in directions determined by the internal architecture of the limestone, following pathways that won't be fully revealed for thousands of years to come. Movile Cave, Romania. Something impossible happened in 1986 near the Black Sea coast of Romania. Construction workers digging a foundation discovered what scientists now call Earth's most extraordinary biological time capsule. Behind a thin limestone wall, sealed for 5.5 million years, an entire ecosystem had been living and evolving in complete isolation from the surface world. No sunlight had ever touched this place. No surface water had ever flowed through its passages. Yet life had not just survived here, it had thrived in ways that challenged everything biologists thought they knew about how ecosystems work. The mystery began when Cristian Lascu, a Romanian speleologist, followed the workers' discovery into a narrow shaft that led into darkness. What he found defied logic. The air reeked of hydrogen sulfide, a gas that kills most surface life. The water was toxic, loaded with chemicals that would poison any normal ecosystem. The temperature held steady at 77 degrees Fahrenheit, far warmer than typical caves. But floating on the surface of those poisonous pools were mats of white thread-like bacteria. And crawling through those bacterial mats were creatures unlike anything science had ever documented. Lascu named it Movile Cave, after the nearby village. But this was no ordinary cave. At only 240 meters long and covering just 12,000 square meters, it represented something unprecedented in the history of life on Earth. Here was proof that complex ecosystems could exist entirely without sunlight, feeding not on photosynthesis, but on chemical energy drawn from the planet's interior. It was the first terrestrial ecosystem ever discovered that operated purely on chemosynthesis, the same process that powers life around deep ocean hydrothermal vents. The discovery sent shockwaves through the scientific community. In 1990, Romanian microbiologist Serban Sabu began the first systematic study of Movile's ecosystem. What he found challenged fundamental assumptions about the requirements for complex life. The cave's food web began with bacteria that could eat hydrogen, sulfide, and methane seeping from deep underground sources. These chemosynthetic bacteria formed the base of a food pyramid that supported an entire community of evolved predators and scavengers. Sabu's initial biological surveys revealed creatures that looked like science fiction. Transparent spiders with elongated legs wandered through the darkness, their eyes reduced to useless remnants. Water scorpions with pale, ghostly bodies hunted in the toxic pools. Centipedes with enhanced sensory organs navigated by touch and chemical signals. Every species showed adaptations to life in perpetual darkness, but these weren't recent changes. The morphological modifications Sabu documented required millions of years of evolutionary pressure. The bacterial mats that covered the cave's pools and walls became the focus of intense biochemical investigation. Scientists discovered that different species of bacteria had specialized in metabolizing different chemical compounds. Some consumed hydrogen sulfide, converting it into energy and sulfur compounds. Others fed on methane seeping from deep rock formations. Still others processed ammonia and nitrites, creating a complex chemical cycle that sustained the entire ecosystem without any input from the surface world. By 1994, detailed species inventories revealed the true scope of Movile's biological uniqueness. Scientists had identified 48 distinct species living in the cave, with 33 of them found nowhere else on Earth. These weren't simply cave-adapted versions of surface species. DNA analysis revealed that many had been evolving independently for millions of years, developing unique genetic characteristics that reflected their isolation from surface gene pools. The cave's water chemistry provided crucial clues to its ancient history. Geochemical analysis showed that the groundwater feeding Movile's ecosystem came from deep aquifers that had been sealed off from surface water for geological ages. Isotope studies of the water revealed that it had been underground since the late Miocene epoch, when the cave system first formed. This water carried dissolved chemicals from rock formations deep in the Earth's crust, providing the chemical energy that powered the cave's entire food web. Modern molecular biology techniques have revealed even more extraordinary details about Movile's ecosystem. Genetic sequencing of the cave's bacteria has shown that some species are more closely related to microorganisms found in deep ocean thermal vents than to any surface bacteria. This suggests that chemosynthetic life may have evolved independently in isolated underground environments around the world, creating hidden ecosystems that operate according to completely different biological rules. The cave's isolation has been so complete that scientists estimate fewer than 100 people have ever entered it since its discovery. This extreme protection has preserved the ecosystem's integrity, but it has also created unique research challenges. Every scientific expedition must be carefully planned to avoid contaminating the environment with surface microorganisms. Researchers wear special protective equipment and follow strict decontamination protocols to prevent introducing foreign bacteria that could disrupt chemical cycles that have operated unchanged for millions of years. Recent studies using advanced DNA sequencing have revealed that Movile's microbial community is even more complex than originally suspected. Scientists have identified over 30 different types of bacteria, each specialized for specific chemical processes. Some bacteria work together in partnerships, with one species producing compounds that feed another species. These bacterial partnerships have evolved over millions of years, creating a perfectly balanced chemical ecosystem that recycles nutrients with remarkable efficiency. The cave's thermal characteristics provide another window into its deep time story. The consistent temperature comes from geothermal heat rising from the Earth's interior, the same heat source that drives the chemical reactions powering the ecosystem. This thermal stability has been crucial to the cave's biological success, providing the steady conditions necessary for complex chemical cycles to evolve and persist over geological timescales. Temperature measurements throughout the cave reveal subtle variations that correspond to different bacterial communities. Areas with slightly higher temperatures support different species than cooler zones, creating microhabitats within the already specialized cave environment. These temperature gradients, measured in fractions of degrees, have been stable for millions of years, allowing incredibly specific adaptations to evolve. Current research focuses on understanding how Movile's ecosystem might respond to climate change and human activity on the surface. Although the cave is sealed from direct surface influence, subtle changes in regional groundwater chemistry could potentially affect the delicate chemical balance that sustains the entire system. Scientists are monitoring trace elements in the cave's water to detect any changes that might indicate external influences. The study of Movile Cave has implications far beyond understanding one unique ecosystem. The discovery has changed how scientists think about the possibility of life on other planets. If complex ecosystems can evolve and persist in complete isolation from sunlight, feeding entirely on chemical energy from planetary interiors, similar life forms might exist in the subsurface environments of Mars or the moons of Jupiter and Saturn. Every sample taken from Movile Cave represents millions of years of evolutionary experimentation, carried out in conditions more alien than anything found on Earth's surface. The bacteria growing in those toxic pools have been perfecting their chemical processes since before human ancestors walked upright. The pale spiders crawling through the darkness have been adapting to their lightless world since before the first flowers bloomed on the surface above. Antelope Canyon, Arizona. The silence hits you first. Not the empty quiet of a vacant room, but the profound hush of stone that has been holding its breath for millions of years. You're standing at the entrance to a crack in the earth so narrow that two people can barely pass without touching. Yet when you look up, the walls soar 120 feet above your head into a ribbon of sky so thin it seems like an afterthought. The air here tastes different, dusty and ancient, carrying the mineral scent of sandstone that has been weathering under the Arizona sun since before grass grew on this planet. Your footsteps echo strangely in this space, each sound bouncing off the curved walls in patterns that seem to stretch and compress time itself. The acoustics create something close to a whisper gallery, where the softest breath becomes a presence, and your own heartbeat seems unnaturally loud. The walls press close around you, smooth as water-carved marble, their surfaces flowing in waves that catch and hold shadows in ways that make you question whether you're moving forward or standing still. Above you, a shaft of sunlight cuts through the opening like a laser, illuminating particles of dust that dance in the beam like tiny planets orbiting an unseen star. But this light behaves differently here. It doesn't simply illuminate the canyon floor. Instead, it ricochets off the polished sandstone walls, creating secondary reflections that bathe the entire space in an amber glow that seems to come from within the rock itself. Colours that have no names shift across the walls as the sun moves overhead, transforming the canyon into a living kaleidoscope of red, orange, gold, and purple. The walls themselves tell a story that began 190 million years ago, during the Jurassic period, when this entire region lay beneath vast sand dunes that stretched beyond any horizon you could imagine. These weren't the small dunes you might see in a modern desert, but massive sand seas that rivaled the Sahara, their surfaces constantly reshaped by winds that blew across a world where dinosaurs were just beginning to rule the land. Grain by grain, these ancient sands accumulated, layer upon layer, eventually reaching depths of thousands of feet. As you run your hand along the canyon wall, you're touching the compressed remnants of those ancient dunes. The smooth flowing patterns in the sandstone preserve the wind patterns from that primordial world, fossilized ripples that show how air currents moved across landscapes that no human eye has ever seen. The crossbedding you can see in the rock layers reveals the direction of those ancient winds, creating a permanent record of weather systems from an era when the supercontinent Pangaea was just beginning to break apart. The temperature here remains remarkably constant, insulated by the thick sandstone walls from the extremes of the Arizona desert above. While the surface world bakes under summer heat that can reach 115 degrees, the canyon maintains a cooler microclimate that changes only gradually throughout the day. This thermal stability creates subtle air currents that carry scents and sounds in unexpected directions, adding to the sense that normal physical laws don't quite apply in this narrow world. But the canyon you're walking through didn't exist when those sand dunes were forming. The slot canyon itself is a much more recent creation, carved over the past 5 to 6 million years by a force that seems almost impossibly gentle for such dramatic results. Flash floods, rushing down from the mesas above during Arizona's monsoon seasons, have been the primary sculptors of this underground cathedral. Each flood carries sand, gravel and debris that acts like liquid sandpaper, grinding away at the Navajo sandstone grain by grain. The smooth flowing walls around you are carved by water moving at tremendous speed through this narrow channel, but the carving process happens slowly, flood by flood, over millions of years. Each torrent of water followed the path of least resistance, exploiting tiny weaknesses in the rock, gradually widening the crack that became this canyon. The swirling patterns you see in the walls show the spiral motions of these floodwaters, preserving the memory of currents that flowed here centuries ago. During these flash floods, the canyon becomes a rushing river that can rise from ankle deep to wall in minutes, transforming this peaceful passage into a churning torrent. The floods carry enormous amounts of sediment, turning the water into liquid concrete that grinds against the walls with unimaginable force. Yet this violent process creates the smooth, sensuous curves that make the canyon so mesmerizing during calm periods. The sandstone, worn by countless floods, develops a surface so polished it seems almost metallic, reflecting light in ways that solid rock shouldn't be able to achieve. The famous light beams that draw photographers from around the world occur only at specific times of year and specific times of day, when the sun reaches the precise angle needed to send shafts of light deep into the canyon. These beams become visible because of dust particles suspended in the air, tiny fragments of the same sandstone that forms the walls, slowly being worn away by wind and the subtle movements of air through the canyon. Each particle in those light beams represents a microscopic piece of the ongoing erosion process that continues to reshape this space. Standing in one of these light beams creates an almost supernatural experience. The intense illumination makes the dust particles appear to move in slow motion, creating a sense that time itself has thickened. The contrast between the brilliant light and the deep shadows beyond is so extreme that your eyes struggle to adjust, creating moments where you seem to exist in multiple time zones simultaneously. The bright beam holds you in a present moment so intense it becomes timeless, while the shadowed walls around you whisper of eons past and future. The colours that emerge in these light conditions have no equivalent in the outside world. The sandstone contains iron oxides that create the base red coloration, but the interplay of direct and reflected light brings out hues that seem to shift and pulse with their own energy. Photographers describe spending hours waiting for the perfect moment when the light and shadows create combinations that exist nowhere else on Earth. Colours so saturated they seem almost artificial, yet born from the most natural processes imaginable. The canyon's narrowness creates its own weather patterns. Air temperatures can vary by several degrees between the sandy floor and the opening above, creating subtle convection currents that move dust and carry sounds in unexpected ways. These microclimates change throughout the day as the sun's angle shifts, creating different lighting conditions that reveal new details in the rock formations every hour. What appears solid and static in morning light transforms into something fluid and alive as afternoon shadows lengthen. The sound environment here defies ordinary experience. Conversations that would be normal volume outside become intimate whispers that seem to emerge from the walls themselves. The curved surfaces of the canyon create acoustic focusing effects that can make footsteps from around a corner sound as if they're coming from directly overhead. During rare rain events, when water begins to trickle down the walls, the entire canyon becomes a resonating chamber that amplifies each drop into a percussion symphony that seems to emerge from the stone itself. In this place where ancient sands have become stone and water has carved cathedral spaces from solid rock, time reveals itself as something far more fluid than our daily experience suggests. The light that illuminates these walls began its journey from the sun 8 minutes ago, but it illuminates rock formations that began their story 190 million years in the past, shaped by processes that continue in this present moment, creating a future that will unfold over millions of years to come. Kawah Ijen crater, Indonesia. The smell hits you like a physical blow, sharp and metallic, burning your nostrils with the acrid bite of rotten eggs mixed with battery acid. You're standing at the rim of what looks like a vision from another planet, a perfectly circular lake that glows an impossible turquoise blue in the early morning light. The water looks inviting, almost tropical, but this is the most acidic natural body of water on Earth, with a pH level between 0.1 and 0.3, more corrosive than car battery acid. Steam rises from its surface in ghostly tendrils, carrying the sulfurous vapours that make breathing here feel like swallowing razor blades. But it's what happens after dark that transforms this hellish landscape into something beyond imagination. As the sun disappears behind the crater walls, electric blue flames begin to dance across the rocky slopes like liquid lightning. These aren't ordinary flames. They burn with an intensity and colour that seems to violate the laws of physics, flowing like rivers of blue fire down the crater walls, pooling in rocky depressions where they flicker and writhe like living creatures made of pure light. For centuries, local people knew about the strange fires that burned in the night at Kawah Ijen, but they whispered about them in fearful tones, calling them supernatural manifestations, spirits of the underworld made visible. The phenomenon seemed so impossible that early European explorers dismissed local accounts as folklore. Fire, they knew, burned orange or yellow, Blue flames like these belonged in gas burners and laboratory equipment, not in the wild landscapes of a volcanic crater. The first scientific attempts to explain the blue fires began in the 1960s, when Indonesian geologist Kusuma Dinata visited the crater and documented the flames with early photography equipment. His images seemed so unreal that many scientists questioned their authenticity. The colour saturation was so intense, the phenomenon so localised, that it challenged everything volcanologists thought they understood about volcanic activity. Here was fire that burned at temperatures reaching 600 degrees Celsius, yet maintained a colour that suggested much higher temperatures, creating a visual paradox that demanded explanation. Early theories focused on the presence of sulfur in the volcanic gases, but sulfur burns with a pale blue flame only under very specific conditions. The mystery deepened when researchers discovered that the flames only appeared at night and only in certain weather conditions. During the day, the same areas showed no visible combustion, despite continuous gas emissions from the same volcanic vents. Something about the interplay between darkness, atmospheric conditions, and the unique chemistry of Kawah Ijen was creating this otherworldly display. The breakthrough came in the 1990s when French photographer Olivier Grunewald spent months documenting the phenomenon and working with Indonesian scientists to understand its mechanics. Using specialized equipment that could measure gas temperatures and chemical compositions in real time, researchers finally solved the puzzle. The blue flames result from the combustion of sulfuric gases that emerge from cracks in the volcano under extremely high pressure and temperature. These gases, primarily hydrogen sulfide and sulfur dioxide, reach temperatures of 600 degrees Celsius as they escape from deep within the Earth. But temperature alone doesn't explain the blue colour. The secret lies in the chemical composition of the burning gases and the specific conditions inside the crater. When sulfur-rich gases combust in the presence of oxygen at these extreme temperatures, they produce light wavelengths that human eyes perceive as electric blue. The intensity of the colour comes from the high concentration of sulfur compounds and the complete combustion that occurs when the gases meet the oxygen-rich air at the surface. The crater itself tells a story that reaches back hundreds of thousands of years. Kawah Ijen formed as part of the Ijen volcano complex in East Java, created by the ongoing collision between the Australian and Eurasian tectonic plates. This collision zone, known as the Sunda Arc, has been producing some of the world's most active volcanoes for millions of years. The specific crater that contains the acid lake and produces the blue flames is relatively young in geological terms, probably less than 10,000 years old, formed by a series of explosive eruptions that hollowed out the current bowl-shaped depression. The acid lake that fills the crater represents one of the most extreme environments on Earth. With a volume of 36 million cubic meters, it contains enough sulfuric acid to dissolve metals instantly. The lake's temperature hovers around 60 degrees Celsius, heated by continued volcanic activity beneath the crater floor. The turquoise colour comes from dissolved minerals, primarily sulfur compounds and metal sulfates, creating a chemical soup that would be lethal to any life form that attempted to survive in its waters. Underground, a complex system of magma chambers and gas vents feeds the surface manifestations that make Kawah Ijen so extraordinary. Hot magma, located several kilometers below the crater, heats groundwater and creates the high-pressure steam that carries sulfur compounds toward the surface. As this sulfur-rich steam travels upward through cracks and fissures in the volcanic rock, it cools and condenses, forming the liquid sulfur deposits that local miners have been harvesting for generations. The mining operation at Kawah Ijen adds a human element to this geological drama that spans millennia. Miners descend into the crater before dawn, wearing minimal protection against the toxic gases, and extract solidified sulfur from areas where the blue flames burn strongest. They carry loads weighing up to 80 kilograms up the steep crater walls, repeating this dangerous journey twice daily. The sulfur they harvest forms when the volcanic gases cool and condense, creating bright yellow deposits that have been accumulating for thousands of years. Modern monitoring equipment has revealed that the blue flame phenomenon varies in intensity based on factors that scientists are still working to understand completely. Wind patterns affect gas flow and combustion efficiency. Atmospheric pressure influences how the gases behave when they reach the surface. Even the pH level of the acid lake seems to correlate with flame intensity, suggesting complex interactions between different aspects of the volcanic system. Recent research using thermal imaging cameras has shown that the blue flames are just the visible portion of a much larger combustion process. Infrared sensors detect heat signatures that extend far beyond the areas where flames are visible to the naked eye, indicating that gas combustion occurs throughout the crater, with the blue flames representing only the most intense burning zones. This invisible fire burns continuously, day and night, creating a hidden landscape of combustion that operates according to principles that scientists are still working to fully understand. The timing of your visit determines what you will experience in this alien landscape. During pre-dawn hours, when atmospheric conditions are most favourable, the blue flames reach their maximum intensity, creating a light show that seems to transform solid rock into flowing rivers of fire. As sunrise approaches and atmospheric conditions change, the flames become less visible, though the gas emissions continue at the same rate. By full daylight, the flames disappear entirely from human perception, though thermal sensors confirm that the combustion process never stops. Standing here in the sulphurous darkness, watching blue fire flow like water across rocks that formed when Java itself was taking shape, you're witnessing the intersection of deep geological time and human perception. The magma heating this system began its journey toward the surface millions of years ago. The chemical reactions creating these impossible flames operate according to laws that have remained constant since the Earth formed. Yet the specific combination of conditions that produces this exact phenomenon exists nowhere else on our planet, making Kawah Ijen a singular point where the planet's deep processes reveal themselves in ways that challenge our understanding of what's possible in the natural world. Bloodfalls, Antarctica. In February 1911, Australian geologist Thomas Griffith Taylor was exploring a desolate valley in Antarctica when she encountered something that shouldn't exist. A waterfall of what appeared to be blood poured from the snout of a glacier, staining the pristine white ice with streams of dark crimson that looked like an open wound in the Earth's frozen skin. Taylor was part of Robert Falcon Scott's Terra Nova expedition, a journey that would end in tragedy, but his discovery of this impossible phenomenon would puzzle scientists for the next century. The waterfall emerged sporadically from Taylor Glacier, sometimes flowing for days, other times remaining frozen for months. When it flowed, the liquid was thick and viscous, more like blood than water, with a metallic taste that burned the tongue and a smell that reminded observers of old pennies left in the rain. Early theories suggested the red colour came from algae, a logical explanation for the time, but algae requires sunlight, and this waterfall emerged from deep within a glacier where no light had penetrated for thousands of years. For decades, bloodfalls remained a curiosity mentioned in expedition reports and scientific papers, but no one could mount a serious investigation. Antarctica was too remote, too dangerous, and the technology needed to analyse the phenomenon properly didn't exist. The mystery deepened during subsequent expeditions when researchers discovered that the red water had an unusually high salt content, nearly 4 times saltier than seawater, and contained concentrations of iron that made it toxic to most forms of life. The first breakthrough came in the 1960s when improved chemical analysis revealed that the red colour indeed came from iron oxide, essentially rust, but this only deepened the puzzle. Where was the iron coming from, and what was causing it to oxidise in an environment that should be oxygen poor? The glacier above Bloodfalls was estimated to be over 400 feet thick, effectively sealing off any contact with the atmosphere. Yet somehow iron was not only present in massive quantities, it was being oxidised at a rate that suggested active chemical processes. By the 1970s, researchers had established that the water emerging from Bloodfalls came from a subglacial source, but drilling through the glacier to reach that source was technically impossible with the equipment available. Scientists could only collect samples when the falls were actively flowing, analysing the chemistry of water that had travelled through unknown pathways from mysterious depths. Each analysis revealed new puzzles. The water contained sulfur compounds typically associated with deep earth processes and isotope ratios that suggested the water had been isolated from surface environments for an extraordinarily long time. The scientific revolution that would finally explain Bloodfalls began in 2003 when Jill McCookie, a microbiologist at Harvard University, first saw photographs of the phenomenon during her graduate studies. McCookie recognized something that earlier researchers had missed. The conditions at Blood Falls, while hostile to most life, might be perfect for extremophiles, organisms that thrive in environments that would kill conventional life forms. She proposed that the red colour might not just be the result of chemical processes, but of biological activity. Getting permission to collect samples from Blood Falls required years of planning and negotiation with international Antarctic research authorities. When McCookie finally reached Taylor Glacier in 2006, she used sterile techniques to collect water samples during one of the fall's active periods. What she found when she analysed those samples back in her laboratory changed our understanding of where life can exist on Earth. The water was teeming with microorganisms, but these weren't ordinary bacteria. DNA analysis revealed at least 17 different types of microbes that had been living in complete isolation beneath the glacier for an estimated 1.5 million years. These organisms had evolved to survive in conditions that would be lethal to surface life. No sunlight, no oxygen, temperatures below freezing, and water so salty and acidic it could dissolve metal. Most remarkably, they had created their own ecosystem feeding on sulfur and iron compounds in a process that generated the very iron oxide that gave the falls their bloody colour. McCookie's discovery revealed that the microorganisms were using a form of metabolism that scientists call anaerobic respiration, essentially breathing sulfur instead of oxygen. As they consumed organic matter trapped in the ancient ice, they produced iron in its ferrous form. When this iron-rich water reached the surface and contacted oxygen in the atmosphere, it oxidized instantly, creating the dramatic red coloration that had puzzled observers for nearly a century. But the biological mystery was only part of the story. In 2017, a team led by Jessica Badgley at Colorado College used ground-penetrating radar to map the subglacial environment that supported this ancient ecosystem. The imaging revealed an extensive network of liquid channels within the supposedly solid glacier, connecting Blood Falls to a large subglacial lake that had been sealed off from the surface for millions of years. The radar data showed that this hidden hydrological system was far more complex than anyone had imagined, with channels that allowed the iron-rich brine to flow through the glacier in patterns that changed with seasonal temperature variations. The subglacial lake that feeds Blood Falls is now understood to be a remnant of ancient seawater that became trapped when the glacier formed millions of years ago. As the ice thickened over geological time, the trapped water became increasingly concentrated, reaching salt levels that prevent it from freezing even at temperatures well below zero. This hypersaline environment became a refuge where ancient marine microorganisms could survive and evolve in complete isolation from the changing world above. Current research using advanced radar imaging has revealed that the Blood Falls system is even more extensive than previously thought. The subglacial brine network extends for miles beneath Taylor Glacier, connecting multiple lakes and representing one of the most unusual hydrological systems on Earth. Recent drilling projects have confirmed that the microbial communities throughout this network are thriving, creating what amounts to an underground ocean of life in one of Earth's most inhospitable environments. The implications of the Blood Falls discovery extend far beyond Antarctica. The microorganisms living in this system represent some of the most ancient genetic lineages on Earth, providing insights into how life might have survived during ice ages and other periods of extreme climate change. More intriguingly, the discovery has influenced how scientists think about the possibility of life on other planets, particularly Mars and the ice-covered moons of Jupiter and Saturn, where similar subglacial environments might exist. Modern studies of Blood Falls continue to reveal new aspects of this extraordinary ecosystem. Recent genomic analysis has shown that the microorganisms have maintained genetic diversity despite their isolation, suggesting that their populations are larger and more stable than initially estimated. Researchers have also discovered that the microbial communities change seasonally, becoming more active during the Antarctic summer when slightly warmer temperatures increase the flow of brine through the glacier. Standing before Blood Falls today, watching crimson water emerge from pristine white ice, you're witnessing the intersection of multiple timescales that challenge human comprehension. The ice above formed from snowfall that accumulated over thousands of years. The water itself has been trapped beneath the glacier for over 1 million years, carrying chemical signatures from ancient seas that covered this region when Antarctica was part of the supercontinent Gondwana. The microorganisms creating the red colour represent genetic lineages that may date back billions of years to the very dawn of life on Earth. Yet this ancient system continues to evolve, its chemistry and biology changing in response to processes that operate on human timescales as well as geological ones. The red stains on the ice represent moments when deep time breaks through to the surface, when processes that have been operating in darkness for millions of years suddenly become visible, reminding us that even in Earth's most frozen and lifeless-seeming places, life finds ways to persist, adapt, and endure. Salar de Uyuni, Bolivia, you're walking across what appears to be the edge of the world. The horizon line has vanished, dissolved into a seamless blend of white salt and endless blue that makes it impossible to tell where the Earth ends and the sky begins. Your footsteps crunch on crystalline formations that catch the morning light like scattered diamonds, each one a perfect hexagon formed by chemical processes that follow rules older than human civilization. Above you, clouds drift across a sky so vast it seems to curve downward at the edges, while beneath your feet, an identical sky stretches into infinity, reflected in the thinnest possible layer of water that transforms this ancient landscape into the world's largest mirror. This is Salar de Uyuni during the rainy season, when a film of water no more than a few centimeters deep covers 4,000 square miles of the Bolivian Altiplano, creating an optical illusion so perfect it defies the brain's ability to process what the eyes are seeing. But this mirror effect, stunning as it appears, represents only the most recent chapter in a story that reaches back through multiple layers of time, each one written in salt that accumulated grain by grain over thousands of years. The water beneath your feet fell as rain just days or weeks ago, part of Bolivia's summer rainy season that runs from December to April. This seasonal flooding happens every year, transforming the blindingly white salt desert into a reflective surface that photographers travel thousands of miles to capture. But the timing of these floods follows patterns established by climate cycles that have operated for millennia, part of larger atmospheric rhythms that govern rainfall across the entire Altiplano. Strip away the seasonal cycle, and you encounter the first deep layer of time that shaped this landscape. The perfectly flat surface you're standing on formed over the past 10,000 years as the last of the great Pleistocene lakes evaporated, leaving behind the salt deposits that create today's mirror. But this wasn't a gradual, steady process. The evaporation happened in stages, with periods of drying interrupted by brief returns of wetter conditions, each cycle leaving its own signature in the salt layers buried beneath your feet. The flatness itself tells a story of time operating at geological scales. Salar de Uyuni varies in elevation by less than 1 meter across its entire 4,000 square mile surface, making it one of the flattest places on Earth. This extraordinary levelness resulted from the way lakes behave over long periods. As ancient Lake Tauca evaporated, it left behind a surface that had been shaped by tens of thousands of years of wave action, currents, and sediment deposition. The final evaporation process preserved that ancient lake bottom, creating a surface so flat that modern satellites use it to calibrate their altimeters. Dig deeper into the geological record, and you discover that Lake Tauca was itself just the most recent in a series of massive lakes that filled and emptied this basin repeatedly during the ice ages. Before Lake Tauca, there was Lake Minchin, which reached its maximum extent around 46,000 years ago. These ancient lakes were enormous, covering not just the current salar but vast areas of the surrounding Altiplano, connected by rivers and straits that transformed the high Andes into an inland sea. The salt crystals crunching beneath your boots contain chemical signatures from all these ancient lakes, preserved in layers that record changing conditions over tens of thousands of years. Drill cores taken from the Salar reveal bands of different coloured salt, each one representing a different period in the basin's history. Some layers formed when the lakes were deep and fresh, others when they became shallow and saline. The chemistry of each layer tells a story about the climate, the volcanic activity, and even the types of organisms that lived in the ancient waters. But the story extends much deeper than the Pleistocene lake cycles. The basin itself formed millions of years ago, created by the same geological forces that built the Andes Mountains. As the Nazca Plate pushed beneath the South American plate, it created not just the towering peaks that surround the Salar, but also the structural depression that allowed the ancient lakes to form. The volcanism that accompanied this mountain building process contributed many of the minerals now concentrated in the Salar's brines, including the lithium that makes these salt flats some of the richest mineral deposits on Earth. Standing on the shore of this ancient basin is Tunupa, a dormant volcano that rises 5,321 meters above sea level. Its perfect cone a reminder of the violent geological processes that created this landscape. Tunupa last erupted during the Pleistocene, when the Great Lakes still filled the basin. The volcano's slopes show evidence of ancient shorelines, horizontal bands etched into the mountainside that mark the different levels reached by lakes that dried up thousands of years ago. These shorelines provide a vertical timeline, with the highest marks representing the maximum extent of the ancient lakes, and lower lines showing the gradual process of evaporation that created the modern Salar. The water creating today's mirror effect carries forward this deep history in dissolved form. The thin layer reflecting the sky contains minerals that have been concentrating in this basin for millions of years, creating brines so rich in lithium, potassium, and other elements that they represent one of the world's most valuable mineral resources. Each raindrop that contributes to the mirror effect picks up these ancient minerals, becoming part of a solution that contains the chemical essence of deep geological time. Modern flamingos wading through the mirror waters are part of an ecological story that connects the present directly to these ancient processes. The brine shrimp and algae that the flamingos feed on can only exist because of the specific chemical conditions created by millions of years of evaporation and mineral concentration. These organisms have evolved to thrive in water so salty it would kill most life forms, creating an ecosystem that depends entirely on the geological processes that shape the Salar. The mirror effect itself operates according to principles that haven't changed since light first reflected off water. The optical perfection requires specific conditions. The water must be absolutely still, with no wind to disturb the surface, and the depth must be just right, deep enough to create a reflective surface but shallow enough to remain perfectly level. These conditions occur only during brief periods when the seasonal rains have stopped, but evaporation hasn't yet removed all the water, creating windows of perhaps a few weeks each year when the Salar becomes a perfect mirror. During these mirror periods, the psychological effects can be profound. Visitors often report a sense of floating in space, disconnected from normal spatial references. The horizon disappears completely, creating a world where up and down lose their meaning. This disorientation connects to something fundamental about how humans perceive time and space, suggesting that our normal sense of being grounded in a particular place and moment depends on visual cues that the mirror eliminates. Current climate change adds another layer to this temporal story. Scientists monitoring the Salar have detected subtle changes in the timing and duration of the rainy seasons, alterations that could affect not just the mirror phenomenon, but the entire chemical balance of the system. Rising temperatures are increasing evaporation rates, potentially concentrating the brines more rapidly than in the past. These changes operate on human timescales, measurable in decades, but they interact with geological processes that operate over millions of years. The increasing demand for lithium, driven by the global transition to renewable energy and electric vehicles, represents the newest chapter in the Salar's story. Mining operations that extract lithium from the ancient brines are connecting this remote Bolivian landscape to technological changes happening worldwide, creating economic and political pressures that will shape how this landscape is used in the future. The lithium now being extracted from the Salar accumulated over millions of years of geological processes, but it's being removed and used on human timescales, creating a collision between deep time and technological time that will define the Salar's future. Cave of Crystals, Mexico. On April 26, 2000, brothers Juan and Pedro Sanchez were drilling 290 meters beneath the Chihuahuan Desert when their equipment broke through into a void that shouldn't have existed. What they found on the other side defied every law of physics and chemistry they thought they understood. A horseshoe-shaped chamber stretched before them, its floor, walls, and ceiling studded with translucent white crystals so massive they seemed like the work of giants. Some crystals measured 36 feet long and weighed over 55 tons, larger than the ancient sequoias of California, but made entirely of selenite gypsum, a mineral that typically forms crystals no bigger than a fingernail. For the first few moments, the brothers could only stare. The crystals crossed the chamber like frozen lightning bolts, creating a maze of translucent pillars that seemed to glow with their own inner light. Some crystals were perfectly clear, others milky white, all of them smooth as glass and sharp enough to cut flesh. The air was thick and stifling, with temperatures reaching 136 degrees Fahrenheit and humidity levels near 100%, creating conditions so extreme that human survival required special cooling suits and breathing apparatus. Within hours of the discovery, word spread through the scientific community like wildfire. Geologists and crystallographers from around the world began making pilgrimages to the Nika mine, each hoping to understand how nature had created what seemed impossible. Gypsum crystals simply don't grow to such sizes. The mineral is soft and water-soluble, typically forming small, delicate structures that dissolve easily in water. Yet here were crystals that had not only grown to enormous proportions, but had maintained their perfect crystalline structure for what appeared to be hundreds of thousands of years. The first theory seemed reasonable enough. Perhaps the crystals had grown in a dry environment, protected from the water that would normally dissolve them. But chemical analysis quickly disproved this idea. The crystals contained fluid inclusions, tiny pockets of ancient water trapped inside the selenite during formation. This meant the crystals had grown while completely submerged, making their size even more mysterious. Spanish crystallographer Juan Manuel Garcia Ruiz arrived at Nika in 2001, determined to solve the puzzle. His initial investigations revealed conditions that challenged everything scientists thought they knew about crystal formation. The cave's temperature and humidity were so extreme that researchers could only work for 10 minutes at a time before requiring evacuation. Specialized cooling suits were developed, but even with this protection, the human body began shutting down after brief exposure to the cave's hellish conditions. Garcia Ruiz's team began analyzing the fluid inclusions trapped within the crystals, hoping these ancient water samples would reveal the conditions under which the crystals formed. What they found deepened the mystery. The inclusions contained water with very specific mineral concentrations, suggesting the crystals had grown in solutions that remained chemically stable for extraordinarily long periods. But maintaining such stability seemed impossible given the dynamic nature of groundwater systems. The breakthrough came when researchers realized they were thinking about the problem backwards. Instead of asking why the crystals were so large, they should have been asking why they weren't larger. Garcia Ruiz's team discovered that the cave sat directly above a magma chamber that had been maintaining the water temperature at exactly 58 degrees Celsius for over 500,000 years. This wasn't just warm water, it was water heated to the precise temperature where gypsum crystals dissolve most slowly. The chemistry was elegant in its simplicity. The underground water was saturated with calcium sulfate, the chemical components of gypsum. At temperatures above 58 degrees, the dissolved minerals remained in solution. But when the water cooled even slightly, below this critical threshold, the excess minerals began crystallizing out of solution. The magma chamber had been maintaining the temperature at exactly this transition point, creating conditions where crystal growth occurred at the slowest possible rate. Slow growth was the key to the crystal's impossible size. In normal crystal formation, rapid growth creates many small crystals as nucleation sites compete for available minerals. But in the cave of crystals, the mineral solution was only barely supersaturated, allowing just a few crystals to form and grow slowly over hundreds of thousands of years. Each crystal grew grain by grain, molecule by molecule, maintaining perfect crystalline structure because the growth rate was so slow that each new layer had time to organize itself perfectly. The temperature stability required for this process defied probability. Underground temperatures typically fluctuate with changes in groundwater flow, seasonal variations, and volcanic activity. But the Nika system had maintained its critical temperature for an estimated 500,000 years, protected by the specific geology of the region and the consistent heat output of the underlying magma chamber. This thermal stability was so precise that variations of even a few degrees would have prevented the giant crystals from forming. Further research revealed that the crystals' growth had stopped and started multiple times over their formation period. Analysis of growth rings within the crystals showed periods of rapid growth alternating with periods of near dormancy, corresponding to subtle changes in the cave's chemistry over geological timescales. Each ring represented thousands of years of accumulation, creating a chronological record of the cave's environmental history encoded in selenite. The discovery raised new questions about crystal formation throughout the solar system. If such enormous crystals could grow under specific conditions on Earth, similar formations might exist in the subsurface environments of other planets and moons. The precise temperature and chemical conditions required for the Nika crystals seemed impossibly specific, yet they had persisted for 500,000 years, suggesting that such conditions might be more common in planetary interiors than previously thought. Modern analysis using electron microscopy and X-ray crystallography has revealed the atomic-level perfection of the Nika crystals. Despite their enormous size, the crystals maintain crystalline structure so perfect that they approach theoretical ideals for gypsum formation. This perfection results from the incredibly slow growth rate, which allowed each molecule to find its optimal position within the crystal lattice without the defects that typically occur during rapid crystallization. In October 2015, the story of the Cave of Crystals took a dramatic turn. The Nika Mining Company ceased operations, shutting down the pumps that had kept the cave dry since its discovery. Within months, the chamber began reflooding with the same mineral-rich water that had created the crystals over the past 500,000 years. The cave is now completely submerged again, returning to the conditions under which the giant crystals first formed. This reflooding created a natural experiment that scientists are monitoring closely. The water temperature remains at the critical 58-degree threshold, meaning the existing crystals are neither growing nor dissolving significantly. They exist in a state of near equilibrium, their growth essentially paused until geological or volcanic changes alter the cave's thermal balance. Some researchers speculate that new crystals might begin forming in the reflooded cave, but such growth would occur over time, scales measured in thousands of years. The Cave of Crystals now exists in a state of suspended animation, its giant crystals growing imperceptibly in darkness and silence, following chemical laws that have operated unchanged since the cave first flooded 500,000 years ago. The precise conditions that created these impossible formations continue to exist, hidden beneath hundreds of feet of water and rock, where temperature and chemistry maintain a balance so perfect that molecules of calcium sulfate continue their ancient dance of dissolution and crystallization. Fairy circles, Namibia, across 2,000 kilometers of the Namib Desert, from southern Angola to northern South Africa, millions of perfectly circular patches of bare earth dot the landscape like giant polka dots on nature's canvas. These mysterious formations, called fairy circles, range from 2 to 12 meters in diameter, each one surrounded by a ring of grass that grows more vigorously than anywhere else in the surrounding desert. From the air, they create patterns so regular and geometric they seem artificial, as if some cosmic designer had laid out a vast template across one of Earth's oldest deserts. For decades, local people offered their own explanations for these strange circles. Some said they were the footprints of gods walking across the desert. Others claimed they marked spots where underground spirits danced, killing the grass with their supernatural energy. The most persistent legend suggested they were created by poisonous dragons' breath, seeping up from deep caverns beneath the sand. But no legend could explain why the circles appeared in such regular patterns, spaced with mathematical precision across hundreds of thousands of square kilometers. The first scientific observations began in the 1970s when researchers flying over the Namib noticed the formations from aircraft and began photographing them systematically. The patterns were unlike anything documented in ecological literature. The circles maintained consistent spacing regardless of local conditions, suggesting some underlying organizing principle that operated independent of topography, soil chemistry, or rainfall patterns. Early surveys revealed that the circles were not random but followed specific rules. Smaller circles were spaced closer together, larger ones farther apart, creating a hierarchy of patterns that seemed to emerge from invisible mathematical laws. Initial theories focused on soil chemistry. Researchers hypothesized that toxic compounds might be seeping up from underground, creating sterile zones where nothing could grow. Extensive soil sampling was conducted throughout the 1980s, with scientists analyzing hundreds of samples for toxic metals, radioactive materials, and various poisonous compounds. But the soil inside the circles proved to be chemically identical to the soil outside them, ruling out toxicity as an explanation. Plant pathologists then proposed that the circles might be caused by plant diseases, perhaps fungal infections that spread in circular patterns from initial infection points. This theory seemed promising because many plant diseases do create circular patterns of death, expanding outward from central infection sites. But detailed analysis of dead vegetation within the circles found no evidence of disease organisms. The plants hadn't died from infection, they had simply failed to grow in these specific locations. In the 1990s, researchers began to notice something curious about the circle's hydrology. During rare desert rainstorms, water that fell on the bare soil inside the circles didn't soak in immediately but instead flowed toward the edges where the ring of vigorous grass grew. This observation led to the first systematic measurements of soil permeability and water retention throughout the fairy circle landscape. Scientists discovered that the soil inside the circles was more compacted than surrounding areas, causing rainfall to run off toward the vegetated rings where plants could access it more efficiently. The breakthrough that would reshape scientific understanding of fairy circles came in 2013 when Norbert Jürgens from the University of Hamburg published research identifying a specific culprit, sand termites of the species Samotermus allocerus. Jürgens had spent over 30 years studying the fairy circle phenomenon, conducting extensive fieldwork throughout the Namib Desert. His investigations revealed that sand termite colonies were present beneath virtually every fairy circle, and that these termites were systematically destroying grass roots within circular territories around their nests. Jürgens' termite hypothesis provided a compelling explanation for the circle's formation and maintenance. The termites, he argued, created the bare patches by killing vegetation in circular zones around their colonies, then benefited from the increased water runoff that concentrated moisture in underground chambers where the termites lived. The regular spacing of the circles reflected the territorial behavior of the termite colonies, with each colony maintaining an optimal distance from its neighbors to avoid competition for resources. The termite theory gained widespread scientific acceptance, but it faced immediate challenges from researchers who questioned whether termites alone could create such perfectly regular patterns. In 2014, Stefan Getzin from the University of Göttingen published competing research arguing that the fairy circles resulted from plant self-organization, a process where vegetation spontaneously arranged itself into regular patterns through competition for water resources. Getzin's mathematical models demonstrated that plants competing for scarce water in arid environments naturally create regularly spaced gaps, forming patterns identical to those observed in the Namib. The debate between termite and plant competition theories intensified when Getzin made a discovery that challenged the termite hypothesis fundamentally. In 2016, he published evidence of fairy circles in the remote Pilbara region of northwestern Australia, over 10,000 kilometres from the Namib Desert. These Australian circles were virtually identical to their African counterparts in size, spacing, and structure, but extensive surveys found no evidence of sand termites or any other social insects that could create such patterns. The Australian discovery forced scientists to reconsider their understanding of fairy circle formation. If termites created the African circles, what was creating identical formations on a different continent in the absence of the proposed causative species? Getzin argued that the similarity between Australian and Namibian fairy circles supported his plant competition theory, demonstrating that identical patterns could emerge through self-organization processes operating under similar arid conditions. Recent research has revealed that the mystery may be even more complex than either competing theory suggests. Advanced soil analysis using isotope tracers has shown that water and nutrient cycling within fairy circles operates according to principles that neither termite activity nor simple plant competition can fully explain. The soil chemistry inside the circles shows evidence of complex microbial communities that may play crucial roles in creating and maintaining the bare patches. Modern remote sensing techniques have allowed researchers to track individual fairy circles over extended periods, revealing dynamic behaviours that earlier studies missed. Some circles grow larger over time, others shrink or disappear entirely. The vegetated rings around circles show seasonal changes in growth patterns that correlate with subtle variations in soil moisture and temperature. These observations suggest that fairy circles are not static formations, but dynamic systems that respond to environmental changes in ways that challenge simple explanations. Current research using ground-penetrating radar and advanced soil analysis has revealed subsurface features that may hold new clues to the mystery. Beneath many fairy circles, researchers have detected compacted soil layers and altered root networks that extend far deeper than previously imagined. These subsurface structures suggest that the processes creating fairy circles may operate on multiple scales simultaneously, involving interactions between termites, plants, soil microorganisms, and hydrological processes that play out over decades or centuries. The fairy circle phenomenon has also been documented in other arid regions, including parts of Australia, Madagascar, and possibly the southwestern United States, suggesting that whatever creates these patterns operates according to universal principles that apply wherever specific environmental conditions occur. Each new discovery of fairy circles in different locations provides additional data for testing competing theories, but it also reveals new complexities that simple explanations cannot address. Today, scientists acknowledge that fairy circles likely result from multiple interacting processes rather than a single cause. Termites may create the initial disturbance patterns, while plant competition and self-organization maintain and regulate the circles over longer time periods. Soil compaction, water flow, and microbial activity may all contribute to sustaining the bare patches once they form. The regular patterns may emerge from the interaction of all these processes operating at different spatial and temporal scales. Hel Turkmenistan. For centuries, Turkmen nomads crossed the vast expanse of the Karakum Desert with their herds, following ancient routes between watering holes and seasonal pastures. The desert they knew was harsh but predictable, a landscape of sand dunes and scattered vegetation, where survival depended on reading subtle signs of wind, weather, and the underground water that occasionally surfaced in rare oases. Their ancestors had navigated this terrain for over 1,000 years, developing an intimate knowledge of every hidden spring and dangerous passage. But nothing in their oral traditions prepared them for what would emerge from the earth in 1971. The Turkmen called their desert Black Sands, and they knew it held secrets beneath its surface. Old shepherds told stories of places where the ground felt warm underfoot, where strange smells rose from cracks in the earth, and where sometimes flames flickered mysteriously from the soil before disappearing again. These were considered spiritual places, touched by jinn or other supernatural forces, to be approached with caution and respect. But the traditional knowledge that had guided nomadic life for generations couldn't explain what was about to unfold near the small village of Darvaza. In the spring of 1971, a team of Soviet geologists arrived in the desert with equipment the locals had never seen before. The expedition was part of the USSR's ambitious plan to map and exploit natural gas reserves throughout Central Asia, a massive undertaking that reflected the Soviet Union's confidence in its technological ability to extract wealth from even the most remote landscapes. The team set up their drilling rig near Darvaza, following geological surveys that suggested significant natural gas deposits lay beneath the desert floor. The drilling proceeded normally for several weeks, with the Soviet engineers following standard procedures for natural gas exploration. Local Turkmen watched from a distance as the massive drilling apparatus worked around the clock, boring deeper into the earth than anyone had ever penetrated in this region. The engineers were confident, experienced in similar operations throughout the Soviet Union, and they had no reason to expect anything unusual from what appeared to be a routine geological survey. Then, on a morning that began like any other, everything went wrong. As the drill bit reached a depth of several hundred meters, it suddenly broke through into a massive underground cavern filled with natural gas under tremendous pressure. The ground beneath the drilling rig gave way catastrophically, swallowing the expensive equipment in a collapse that created a crater 70 meters wide. Methane gas began pouring from the newly opened chasm at dangerous levels, creating an invisible toxic cloud that made the area uninhabitable. The Soviet engineers faced a dilemma that their training hadn't prepared them for. The methane escaping from the crater posed serious risks to nearby villages and wildlife, but the remote location made it impossible to cap the leak using conventional methods. After consulting with their superiors, the team made a decision that seemed logical at the time. They would burn off the escaping gas, expecting it to consume the underground reserves within a few weeks and solve the problem permanently. When they ignited the escaping methane, the resulting flames exceeded every expectation. The entire crater erupted in fire that burned with an intensity and consistency that defied their understanding of natural gas combustion. The flames reached heights of 20 meters, creating a roar that could be heard for miles across the desert. Instead of burning out in weeks as predicted, the fire continued month after month, fed by what appeared to be inexhaustible underground gas reserves. Local Turkmen who witnessed the ignition described a moment when day turned to night as smoke blocked the sun, followed by an otherworldly glow that transformed the familiar landscape into something from their most ancient legends. The constant roar of burning gas created a sound unlike anything in their experience, drowning out the desert's natural silence and replacing it with what seemed like the voice of the underworld itself. As months turned to years and the fire showed no signs of diminishing, the crater began attracting visitors from across the Soviet Union. Scientists, government officials, and curious citizens made pilgrimages to witness what many considered an engineering disaster turned a geological phenomenon. The Soviet media initially tried to suppress information about the accident, but word spread through unofficial channels about the mysterious burning crater in the Turkmen desert. By the 1980s, the crater had become an unofficial tourist destination despite the government's attempts to limit access. Visitors described the hypnotic effect of watching flames dance across the crater's surface, creating patterns that seemed to shift and evolve with their own intelligence. The constant burning had begun to alter the surrounding landscape, heating the ground and creating microclimates that supported vegetation patterns unlike anything seen elsewhere in the Karakum Desert. After the Soviet Union's collapse in 1991, Turkmenistan gained independence, and the crater became more accessible to international visitors. Foreign journalists and scientists began documenting the phenomenon, bringing global attention to what locals had started calling the door to hell. These accounts revealed that the crater's behaviour was far more complex than simply burning natural gas, with flames that varied in intensity and colour depending on atmospheric conditions and underground pressure fluctuations. The most dramatic chapter in the crater's modern history began in November 2013 when Canadian explorer George Kourounis announced his intention to become the first person to descend into the burning crater. Kourounis, an experienced storm chaser and extreme environment specialist, spent months preparing for the descent, working with engineers to develop heat-resistant equipment that could protect him from temperatures exceeding 1,000 degrees Celsius. Kourounis's expedition, supported by National Geographic, represented the culmination of decades of speculation about what lay at the bottom of the crater. His specially designed heat suit and breathing apparatus allowed him to rappel 100 feet down through the flames to reach the crater floor, where he collected soil samples and documented conditions that no human had ever experienced directly. His thermal imaging equipment revealed that the crater's walls were riddled with gas vents of varying sizes, creating a complex system of combustion that explained the fire's remarkable persistence. The samples Kourounis collected revealed microscopic lifeforms that had somehow adapted to survive in conditions that seemed incompatible with biological processes. These extremophile bacteria, thriving in superheated soil saturated with methane and other hydrocarbons, represented forms of life that expanded scientists' understanding of the environments where organisms can exist. The discovery suggested that the crater had become not just a geological phenomenon, but a unique ecosystem shaped by 5 decades of continuous combustion. Recent geological surveys using ground-penetrating radar and seismic monitoring have revealed that the underground gas reservoir feeding the crater is far more extensive than originally estimated. The 1971 drilling accident tapped into a natural gas field that extends for miles beneath the desert, connected to the same geological formations that make Turkmenistan one of the world's largest natural gas producers. This explains why the fire has burned continuously for over 50 years without showing signs of depletion. Today, the Turkmen government faces competing pressures regarding the crater's future. President Gurbanguly Berdimuhamedov announced in 2022 his intention to close the crater, arguing that the continuous burning wastes valuable natural resources that could contribute to the country's economy. However, the crater has become Turkmenistan's most famous tourist attraction, drawing thousands of visitors annually to a country that receives relatively few foreign tourists. Local Turkmen communities have adapted to living near this eternal flame, incorporating it into their cultural narratives while maintaining their traditional nomadic practices. Young shepherds now guide tourists to viewing areas around the crater, combining ancient knowledge of desert survival with modern tourism services. The crater has become a bridge between traditional Turkmen culture and the global economy, transforming a Soviet-era industrial accident into a source of national identity and international recognition. Socotra Island, Yemen. The morning sun rises over a landscape that belongs to no earthly continent. Strange, umbrella-shaped trees dot the rocky plateau like giant mushrooms, their twisted branches spreading in perfect symmetry against a sky that seems borrowed from another planet. These are dragon blood trees, and as the first light touches their waxy leaves, they begin to weep crimson tears, a red resin so vivid it looks like fresh blood flowing from wounded bark. You're standing on Socotra Island, 240 kilometers off the coast of Yemen, witnessing the daily ritual of species that have been performing this same act for over 20 million years. The dragon blood tree you're observing may be 800 years old, its umbrella canopy a masterpiece of evolutionary engineering that captures moisture from the rare fogs that drift across this arid landscape. But its age represents just a fraction of the story written in its DNA. This individual tree connects to an unbroken lineage that extends back to when Socotra itself was part of a very different world, when the island was still connected to the supercontinent that geologists call Gondwana. 20 million years ago, the forces that would create the Red Sea and the Gulf of Aden began tearing apart the ancient landmass that connected Africa and Arabia. As tectonic plates shifted and pulled apart, Socotra became an island, carrying with it a cargo of plants and animals that would evolve in complete isolation from their continental relatives. The dragon blood trees that covered parts of the ancient landscape found themselves marooned on this rocky arc, free to develop into forms that would eventually exist nowhere else on Earth. The geological violence that created Socotra's isolation is still visible in the island's dramatic topography. The Hillier Mountains, rising to 1,500 meters above sea level, represent the uplifted remnants of ancient Precambrian basement rocks that formed over 750 million years ago. These mountains are among the oldest exposed rocks in the Arabian Peninsula, providing a foundation that has remained stable even as the surrounding landscapes underwent massive changes. The granite peaks that dominate the island's interior tell stories of mountain-building episodes that occurred when complex life was just beginning to emerge in Earth's oceans. Below the ancient granite lies an even older story. The basement rocks of Socotra contain minerals and structures that formed during the assembly and breakup of earlier supercontinents, processes that operated hundreds of millions of years before the island's final separation from Arabia. These deep rocks carry chemical signatures from atmospheric conditions and ocean chemistry that existed when the Earth was a fundamentally different planet, with different levels of oxygen, different climate patterns, and different forms of life. The dragon blood trees growing above this ancient foundation represent one of the most remarkable examples of evolutionary isolation on Earth. DNA analysis has revealed that Socotra's flora includes over 300 plant species found nowhere else on the planet, representing an endemism rate of 37%. This means that more than 1/3 of the island's plants evolved entirely in isolation, developing unique characteristics during the 20 million years since the island separated from the mainland. The umbrella shape of the dragon blood trees serves multiple functions that reflect the specific environmental challenges of Socotra's climate. The broad, flat canopy maximizes the tree's ability to capture moisture from fog and rare rainfall, channeling water down the trunk to roots that extend deep into rocky crevices. This architecture evolved over millions of years as the island's climate became increasingly arid, forcing the trees to develop more efficient methods of water collection and retention. The crimson resin that gives the trees their name serves as both protection and communication. When the bark is wounded, the red substance seals the injury, preventing infection and water loss, but the resin also contains chemical compounds that may play roles in protecting the tree from the unique pathogens and insects that evolved alongside it on Socotra. The bright red colour might serve as a warning signal to herbivores, indicating that the tree contains defensive chemicals that make it unpalatable or harmful to eat. Modern genetic analysis has revealed that Socotra's dragon blood trees are most closely related to species found in the Canary Islands and Madeira, suggesting that their common ancestor was distributed across a much wider area when global climate patterns were very different. As climate change and continental drift altered the Mediterranean and Atlantic regions, these relic populations became isolated on islands where they could continue to survive and evolve independently. The island's isolation has created what scientists call an evolutionary laboratory, where natural selection has been able to experiment with forms and strategies that would be impossible in more connected ecosystems. Besides the dragonblood trees, Socotra hosts bottle trees with swollen trunks that store water, cucumber trees that grow to enormous sizes, and desert roses that form natural bonsai gardens in the rocky soil. Each species represents a unique solution to the challenges of island life, developed over millions of years of evolutionary refinement. Current research using satellite imagery and ground-based monitoring has revealed that Socotra's ecosystems are changing more rapidly now than at any time in their recent evolutionary history. Climate change is altering rainfall patterns and increasing temperatures beyond the ranges that many endemic species evolved to tolerate. The dragonblood trees that have survived ice ages and volcanic activity are now facing environmental changes that occur faster than their evolutionary adaptations can respond. The island's human history adds another layer to its temporal complexity. Archaeological evidence suggests that humans first arrived on Socotra around 2,000 years ago, bringing with them domestic animals and agricultural practices that began altering landscapes that had evolved without large herbivores. Traditional Socotra culture developed sustainable relationships with the island's unique ecosystems, but modern development pressures are creating changes that operate on timescales measured in years rather than millennia. Conservation efforts now focus on protecting the approximately 825 plant species documented on Socotra, including the 308 endemic species that exist nowhere else. But protecting these species requires understanding their evolutionary relationships and ecological requirements, knowledge that researchers are still developing. Each endemic species represents millions of years of evolutionary investment, making their loss irreplaceable in terms of biological diversity and evolutionary potential. The dragonblood trees face particular challenges because they reproduce slowly and require specific conditions for seedling establishment. Young trees may take decades to reach maturity, and the adult trees that currently dominate the landscape may represent the last generation that established during more favourable climatic conditions. Climate change could prevent successful reproduction even if the adult trees survive for several more centuries. Modern molecular techniques have revealed that even within Socotra, the dragonblood trees show genetic differences between populations separated by just a few kilometres, indicating that limited gene flow has allowed local adaptation to develop across the island's varied microclimates. This genetic diversity, accumulated over thousands of generations, provides the raw material that might allow the species to adapt to changing conditions, but only if environmental changes occur slowly enough for natural selection to operate effectively. Giant's Causeway, Northern Ireland. Along the rugged coast of County Antrim, where the North Atlantic crashes against ancient cliffs, there exists a pathway that seems carved by hands larger than human. 40,000 stone columns march into the sea like the remnants of some titanic architecture, each one a perfect geometric puzzle piece fitted alongside its neighbours. The local fishermen who have walked these shores for generations still call them by their old name, the Steps of the Giant. Long before science offered explanations, the people of this coast knew these stones intimately. They told stories around peat fires, stories that travelled from cottage to cottage, from father to son, from grandmother to granddaughter. In their tales, this was Clochan Nab Fomhorach, the stepping stones of the giants built by the mighty Fionn mac Cumhail when the world was young and heroes strode across the earth. The old stories say that Fionn was the greatest of all Irish warriors, leader of the Fianna, protector of the High King, but even mighty Fionn had rivals. Across the narrow waters in Scotland lived Benandonna, a giant of such fearsome size that his footsteps shook the mountains. The two had never met, but their challenges echoed across the waters like thunder, each daring the other to cross and settle their rivalry with combat. Fionn's solution was bold beyond measure. He would build a causeway, a bridge of stone that would span the treacherous waters between Ireland and Scotland. Night after night, he laboured, pulling great columns of basalt from the earth's heart, arranging them in perfect order until they formed a road fit for giants. The local people watched in awe as the pathway grew, stone by stone, reaching ever further into the grey northern sea. But when Ben and Donna finally crossed to meet him, Fionn discovered that his rival was larger than he had imagined, a true mountain of a man whose shadow fell across entire valleys. Fionn's wife, Una, clever beyond her husband's brawn, devised a plan. She dressed Fionn as a baby and placed him in an enormous cradle. When Ben and Donna saw the size of what he believed was Fionn's infant son, he fled in terror back to Scotland. In his haste to destroy the causeway behind him, he tore up great sections of the bridge, leaving only the beginning and end, the fragments we see today in Ireland and at Fingal's cave in Scotland. These stories lived in the voices of the people for centuries, but they remained locked within this small corner of the world, known only to those who walked these shores. That began to change in the spring of 1693 when a young clergyman named Samuel Foley made a journey north from his parish in County Wicklow. Foley had heard whispered reports of something extraordinary on the Causeway coast, something that defied easy description. What Foley found when he arrived at the shoreline was beyond anything his education at Trinity College had prepared him for. Thousands upon thousands of stone columns, each one perfectly shaped, most with 6 sides, some with 5 or 7, rising and falling like organ pipes carved from dark volcanic rock. He walked among them for hours, trying to understand what force could have created such geometric precision in nature. Foley was not content to simply wonder. He was a man of his time, caught up in the new spirit of scientific inquiry that was sweeping through Europe. He made careful observations, counting columns, measuring their dimensions, noting the way they fitted together without mortar or binding of any kind. His letters describing the phenomenon reached Sir Richard Bulkeley, a Fellow of Trinity College and member of the Royal Society in Dublin. Bulkeley understood immediately that Foley had discovered something of immense scientific importance. In April of 1693 he wrote to the Royal Society in London, describing these strange basaltic columns in terms that would capture the imagination of natural philosophers across Europe. His account was published in the Philosophical Transactions, and suddenly this remote corner of Ireland became a destination for some of the finest minds of the age. But it was not until the 1740s that the wider world truly saw the Giant's Causeway, thanks to an artist named Susanna Drury. Working with watercolours and gouache, Drury created 2 magnificent paintings of the site, one showing the eastern approach and another capturing the western view. These were not mere illustrations, but works of art that conveyed both the scientific precision and the sublime beauty of the place. When Drury submitted her paintings to the Royal Dublin Society in 1740, they caused a sensation. The Society awarded her their highest premium of £25, an enormous sum at the time, and arranged for the paintings to be engraved and distributed across Europe. For the first time, people in London, Paris and beyond could see exactly what lay on this distant Irish shore. The engravings travelled like wildfire through the intellectual circles of Europe. Natural philosophers debated their meaning in coffee houses, while poets and artists found in them a new vision of nature's power. The great German writer Goethe kept copies in his study, and they influenced his thinking about geology and the formation of the Earth itself. As the 18th century progressed, a steady stream of visitors began making the difficult journey to see the Causeway for themselves. They came by ship from Belfast, braving rough seas and dangerous landings, or travelled overland through bog and mountain, guided by local men who knew the treacherous paths. Each visitor brought their own questions, their own theories about what they were seeing. Some believed the columns were formed by the action of water, carved by countless years of waves and weather. Others suspected crystallization, thinking that some unknown chemical process had caused the rock to form in these perfect geometric shapes. A few even proposed that they were artificial, the work of some ancient civilization whose building techniques had been lost to time. The mystery deepened when travellers reported similar formations on the Scottish island of Staffa, where Fingal's cave displayed the same hexagonal columns arranged in a natural cathedral. Could these be connected somehow? Had the same force that created the Irish Causeway also worked across the water in Scotland? It would take the new science of geology, still in its infancy, to begin unravelling the true story. In the late 18th and early 19th centuries, pioneering geologists like James Hutton and Charles Lyell began to understand that the Earth itself had a history, that rocks could tell stories of ancient times and processes that dwarfed human experience. They discovered that the Causeway was born in fire, not water, 60 million years ago, when the continents themselves were slowly drifting apart, massive volcanic eruptions tore open the earth between what would become Ireland and Scotland. Molten rock, basalt heated to over 1,000 degrees, poured from these fissures in stupendous quantities, covering the landscape in a lake of lava. As this volcanic lake cooled, it contracted, creating enormous stresses in the solidifying rock. Like mud cracking in a dried pond, but on a scale almost impossible to imagine, the cooling basalt fractured in regular patterns. The cracks spread downward through the entire thickness of the lava flow, creating the columns we see today. The hexagonal shape emerged naturally from the physics of contraction, each column representing the most efficient way for the cooling rock to relieve its internal stress. This cooling process took place over thousands of years, at a pace so slow that the rock had time to form these perfect geometries. The columns stand today as a record of that ancient cooling, each one a timeline written in stone, showing us exactly how the Earth's fire became solid rock over geological ages that stretch far beyond human comprehension. The local people who had walked among these stones for generations were not wrong in their intuition that something extraordinary had shaped this place. Their stories of giants and superhuman forces contained a deep truth about the immense powers that had worked here, powers that operated on scales of time and energy that still challenge our understanding. Lake Hillier, Australia, in the age of satellite imagery, when every corner of our planet has been mapped and photographed from space, it still seems impossible that a lake could be the colour of bubblegum. Yet there it sits on Middle Island, off the coast of Western Australia, a perfect circle of pink water surrounded by eucalyptus forest and white sand beaches, as if someone had spilled strawberry milk across the landscape. From overhead, Lake Hillier looks like a wound in the earth, or perhaps a giant's rose petal dropped carelessly among the green trees. The pink is so vivid, so utterly unnatural looking, that early aerial photographers sometimes refused to publish their images, certain that their film had been damaged or their colour processing had gone wrong. The mystery began not with scientists or explorers, but with the simple act of climbing a hill to get a better view. On January 15, 1802, Matthew Flinders, the British navigator who had become famous for circumnavigating and naming Australia, was making his way through the dangerous waters of the Recherche archipelago aboard HMS Investigator. The ship had been at sea for months, charting the unknown southern coast of this vast continent, and Flinders had learned to take advantage of every opportunity to survey the landscape from higher ground. Middle Island rose from the ocean like a green jewel, its forested hills promising fresh water and a chance to repair equipment and rest his weary crew. Flinders came ashore with his botanist Robert Brown and several sailors, intending to climb the island's highest peak to get his bearings and chart the surrounding waters. The climb was steep and difficult through thick scrub, but when they finally reached the summit that would later bear Flinders' name, the view took their breath away. Spread below them was a landscape of such impossible beauty that Flinders struggled to find words for his journal. The ocean stretched endlessly in all directions, dotted with dozens of small islands. Dense forest covered the slopes beneath them, and there, nestled in a clearing not far from where they stood, was a lake unlike anything any of them had ever seen. It was perfectly round, perhaps 400 yards across, and it was bright pink. Flinders wrote in his journal that evening, "I climbed the highest peak on the island to survey the surrounding waters and discovered a small lake of a rose colour, the water of which, as I was informed by Mr. Brown who visited it, was so saturated with salt as to leave crystallised particles upon evaporation. Even in his careful scientific language, the wonder comes through. Here was something that challenged everything they thought they knew about how the natural world worked. The lake seemed to glow in the afternoon sun, its pink surface reflecting the sky in a way that made it appear almost luminous. Brown, trained as a botanist and accustomed to cataloguing the unusual, collected samples of the water and noted the thick crust of salt that had formed around the lake's edges. The water was so salty that it left white crystals on their hands when they touched it, and it had a slightly oily feel that suggested something more than just dissolved minerals. For the next 2 centuries, Lake Hillier remained one of nature's most beautiful unsolved puzzles. Ships occasionally stopped at Middle Island, and every visitor was struck by the same sense of wonder that had captivated Flinders. The lake never changed its colour, never faded or shifted with the seasons. Whether viewed under the harsh midday sun or the soft light of dawn, it remained that same impossible shade of pink, as if someone had mixed watercolour paint with seawater. Scientists proposed theory after theory. Some believed it was iron oxide, rust dissolved in water, giving it a reddish tint. Others suggested it might be due to red algae, similar to what occasionally created red tides in the ocean. A few thought it might be caused by salt-loving bacteria, microorganisms that could survive in the lake's extreme salinity. But without the tools of modern molecular biology, these remained educated guesses rather than definitive answers. The breakthrough began in 2015, when Dr. Ken McGrath, a microbiologist working with the Extreme Microbiome Project, decided to tackle the mystery using the latest techniques in DNA sequencing. McGrath was part of a new generation of scientists who understood that the microbial world held secrets that earlier researchers could never have imagined. With advanced genetic tools, he could identify not just what organisms lived in Lake Hillier, but how they survived in its harsh environment and what role they played in creating its famous colour. McGrath's first challenge was simply getting to the lake. Middle Island is now a protected nature reserve, and access requires special permits and careful coordination with Australian wildlife authorities. When he finally reached the shoreline, he found himself walking in Flinders' footsteps, collecting water samples from the same pink lake that had puzzled visitors for more than 200 years. Back in the laboratory, McGrath and his team began the painstaking process of extracting and analysing DNA from their Lake Hillier samples. What they found was a thriving ecosystem of extremophiles, microorganisms that had adapted to conditions that would kill most other forms of life. The lake's salt concentration reached 28%, nearly 10 times saltier than seawater, and it was severely depleted in phosphates, one of the essential nutrients that most life requires. The DNA analysis revealed that Lake Hillier wasn't coloured by just one organism, but by a complex community of pigment-producing microbes working together. The dominant species was Dunaliella salina, a type of algae that produces bright red carotenoids to protect itself from intense sunlight and salt stress. These are the same pigments that make carrots orange and flamingos pink, concentrated here in quantities that turned an entire lake into a work of natural art. But the algae weren't working alone. Mixed among them were bacteria called halophiles, literally salt lovers, that had evolved their own strategies for surviving in this extreme environment. Species like Salinibacter ruber produced their own red and purple pigments, adding to the lake's colour while playing crucial roles in the ecosystem's chemical cycles. Some of these bacteria were polyextremophiles, organisms capable of surviving not just extreme salinity, but also high radiation levels that would destroy human cells. The most remarkable discovery came when McGrath's team analysed the metabolic pathways these organisms used to survive. In Lake Hillier's harsh environment, normal biological processes wouldn't work. The microbes had evolved entirely new ways of harvesting energy from sunlight, processing nutrients and protecting themselves from chemical damage. Some produced antifreeze proteins to prevent ice crystals from forming in their cells during cold weather. Others manufactured specialized enzymes that could function in the lake's caustic salt-saturated water. These weren't just survivors eking out a marginal existence. The DNA evidence showed that Lake Hillier's microbial community was thriving, with active populations of primary producers, consumers, and decomposers creating a complete self-sustaining ecosystem. The pink colour that had puzzled observers for centuries wasn't just a byproduct of extreme conditions, but an active adaptation that allowed these organisms to flourish in their impossible environment. Modern research has revealed that Lake Hillier represents something far more significant than just a colourful curiosity. The extremophiles living in its pink waters may hold keys to understanding how life could survive on other planets, particularly Mars, where similar high-salt, high-radiation conditions exist. NASA scientists have begun studying Lake Hillier's microbes as potential models for what extraterrestrial life might look like. The lake also serves as a living laboratory for understanding how life adapts to rapidly changing conditions. Climate change and human activity are altering environments around the world, and the strategies that Lake Hillier's organisms use to survive extreme conditions may become increasingly important as other ecosystems face unprecedented stresses. Perhaps most remarkably, recent genetic studies have shown that some of Lake Hillier's microbes can enter cryptobiotic states, essentially stopping all biological processes during particularly harsh periods and then reviving when conditions improve. These organisms exist in a state between life and death, capable of surviving for potentially thousands of years before returning to active metabolism. In Lake Hillier's pink waters, time itself becomes flexible, with entire populations capable of pausing their existence and resuming it in some distant future. Fingal's Cave, Scotland. The first thing you hear is not quite silence, but something deeper than quiet. As your small boat rounds the rocky coastline of Staffa, engines sputtering against the North Atlantic swells, you find yourself listening to something that seems to rise from the stone itself. Even before you see the cave's mouth, the sound reaches you across the water, a low, resonant humming that grows stronger with each wave that crashes against the basalt cliffs. It's as if the island is singing to itself, a deep musical note that vibrates through the water and up through the wooden hull beneath your feet. When Fingal's Cave finally comes into view, your first instinct is to catch your breath and hold it. The entrance yawns before you like the mouth of some primordial cathedral, 70 feet high and perfectly arched, framed by columns of dark basalt that rise from the waterline to disappear into shadow above. The columns stand like organ pipes, each one precisely hexagonal, each one fitted to its neighbours with the kind of mathematical perfection that makes you question whether nature could truly create something so deliberate, so architectural. The boat captain cuts the engine, and in that moment of mechanical silence the cave's true voice emerges. Every sound, every whisper of wind, every splash of water against stone gets caught by those towering basalt walls and transformed into something larger than itself. Your own breathing becomes part of a vast acoustic symphony. The gentle lapping of waves against the boat's hull multiplies into a rhythm that seems to pulse from the very heart of the earth. As you drift closer to the cave's entrance, the scale becomes overwhelming. The columns that looked impressive from a distance now reveal themselves as truly monumental, some rising straight and true for 40 feet or more, others leaning slightly as if they're listening to some conversation taking place deep within the rock. The basalt is not simply black, as it appeared from shore, but reveals subtle variations in colour and texture. Charcoal grey near the waterline where centuries of salt spray have polished the stone, darker midnight hues higher up where the rock remains dry, and occasional streaks of rust red where iron minerals have oxidised in the sea air. The water beneath your boat is so clear that you can see the cave floor 20 feet below, where more basalt columns extend downward, like the roots of some stone forest. Fish move through this underwater colonnade in silver schools, their movements creating brief flashes of light that dance across the submerged stone. The water itself carries sound differently here, conducting the cave's acoustic signature in ways that make every small noise, every creak of the boat, every movement of your jacket, part of the cave's ongoing composition. Drifting into the cave mouth, you enter a world where sound and stone have been dancing together for millions of years. The walls curve away into darkness, but your voice, when you finally dare to speak, returns to you from multiple directions, layered and enriched until it sounds like a choir. The echo is not a simple repetition, but a complex weaving of sound that builds upon itself, creating harmonies and resonances that no human architect could have calculated. This is the sound that stopped Felix Mendelssohn in his tracks on a grey August morning in 1829. The young German composer had travelled to Scotland with his friend Karl Klingemann, part of a grand tour of the British Isles that was meant to broaden his musical horizons. He was 20 years old, already recognised as a prodigy, but nothing in his formal training had prepared him for what he encountered when his boat entered this cave. Mendelssohn carried a small notebook with him always, and he later wrote to his sister Fanny, "In order to make you understand how extraordinarily the Hebrides affected me, I cannot refrain from sending you the following, which came into my head there." On the page, he sketched out a musical phrase, just 20 bars of notes that would eventually become the opening theme of his Hebrides Overture, one of the most beloved pieces in the classical repertoire. But Mendelssohn's musical notation could only capture part of what happens in Fingal's Cave. The acoustics here work on multiple levels, creating what modern sound engineers recognise as a nearly perfect natural amphitheatre. The hexagonal geometry of the basalt columns, the precise curve of the cave's ceiling, the way the water level rises and falls with the tides, all combine to create acoustic properties that amplify and enhance sound in ways that seem almost designed for music. The columns themselves are marvels of natural engineering, each one a testament to the power of slow, patient geological processes. These hexagonal pillars were born 60 million years ago, when this part of Scotland was torn apart by volcanic forces that split the Earth's crust as the Atlantic Ocean began to open. Massive flows of lava poured across the landscape, some of them hundreds of feet thick, cooling slowly over thousands of years. As the lava cooled, it contracted, creating stresses that had to be relieved somehow. The cooling rock began to crack, and those cracks followed the path of least resistance, creating the hexagonal patterns we see today. It's the same geometric principle that creates the cells in a honeycomb, the same mathematical efficiency that appears when soap bubbles cluster together. Nature, given enough time and the right conditions, consistently chooses these patterns because they distribute stress most evenly, creating structures of maximum stability with minimum material. The cave itself was carved much later, sculpted by thousands of years of waves that found the weakness where the lava flow met older rock beneath. Wave after wave, storm after storm, winter after winter, the Atlantic gradually hollowed out this space, polishing the basalt columns smooth and creating the acoustic chamber that exists today. The cave is still being carved, still changing, though at a pace so slow that human visitors see it as eternal and unchanging. Standing in this space, surrounded by columns that took millennia to cool, and by waters that have been shaping this cave for hundreds of thousands of years, you begin to understand why so many visitors have found Fingal's cave spiritually overwhelming. Sir Walter Scott visited in 1814 and wrote of feeling the strange, the almost fearful impression of being in the presence of geological time made visible. The naturalist Sir Joseph Banks, who first brought the cave to scientific attention in 1772, described it as one of the most magnificent natural curiosities in the world. Great Blue Hole, Belize. From 30,000 feet above the Caribbean Sea, it appears as nothing more than a dark blue circle in the lighter blue waters surrounding Lighthouse Reef. Pilots flying between Belize City and the resort islands to the east know this landmark well. A perfect round void in the ocean, 300 feet across, so deep that its waters appear almost black against the turquoise shallows of the reef. Today, tourist boats cluster around its rim like white dots, their passengers peering down into depths that seem to swallow light itself. Divers slip over the sides of their boats and disappear into the blue, following descent lines that vanish into darkness below. This is how the Great Blue Hole presents itself to our modern world, as a destination, a bucket list dive site, a wonder to be photographed and shared on social media. But every ripple on its surface, every shaft of sunlight that penetrates its depths before being absorbed by the darkness below, carries stories that stretch back through layers of time so vast that the human mind struggles to grasp their scale. Watch a diver descend into the hole today, and you're witnessing the latest chapter in a story that began long before humans walked the earth. At 40 feet below the surface, the tropical fish that crowd the reef above begin to thin out. Schools of jacks circle the rim like living clouds, but they rarely venture into the deeper waters. The coral formations that make Belize's barrier reef famous end abruptly at the hole's edge, as if someone had drawn a line in the ocean floor. At 60 feet, the walls of the hole become visible, revealing limestone formations that look almost architectural in their precision. These are not the chaotic, organic shapes of coral growth, but geometric patterns carved by processes that operate on entirely different timescales. The limestone appears grey-blue in the filtered sunlight, marked by horizontal lines and ledges that create a natural staircase descending into the abyss. But step back 100 years to 1971, when Jacques Cousteau first brought his research vessel, Calypso, to investigate this mysterious hole in the sea. Cousteau's team had primitive equipment by today's standards, but they were the first to document what lay in the deeper reaches of the hole. Using a small submarine, they descended past the recreational diving limits and discovered something extraordinary. Massive stalactites hanging from underwater ledges, formations that could only have been created in air, in dry caves, far above the current sea level. These stalactites told a story that challenged everything scientists thought they knew about this part of the Caribbean. Stalactites form when mineral-rich water drips from cave ceilings over thousands of years, building up limestone deposits drop by drop. They can only grow in air, which meant that the Great Blue Hole had once been a dry cave system, its chambers filled with air instead of seawater, its floors walked by creatures that breathed oxygen instead of extracting it from water through gills. Peel back another layer of time, perhaps 15,000 years, to the end of the last ice age. The Great Blue Hole as we know it today did not exist. In its place stood a massive limestone cave system, part of an underground network that honeycombed the bedrock beneath what is now the Caribbean Sea. The cave chambers stretched for hundreds of feet underground, supported by pillars of living rock and decorated with the slowly growing stalactites and stalagmites that marked the patient passage of geological time. Above these caves, the landscape looked nothing like the modern Caribbean. Sea levels were 400 feet lower than they are today, with vast ice sheets locking up water that now fills the world's oceans. Where tourists now see endless blue water, there were forests of cecropia and cohoon palm, grasslands where jaguars hunted giant ground sloths, river valleys where early humans followed game trails through landscapes that would be unrecognizable to us today. The cave system itself was ancient even then, carved from limestone bedrock that had been accumulating for millions of years. This limestone was formed during the Quaternary period, when the area lay beneath a shallow tropical sea teeming with marine life. Countless generations of coral polyps, shellfish, and microscopic organisms lived and died in these ancient waters, their calcium carbonate skeletons settling to the seafloor in layers that gradually compressed into the limestone that would later be carved into caves. The caves were created by a process that continues today throughout the limestone regions of the world. Rainwater, slightly acidic from dissolved carbon dioxide, seeped through cracks in the limestone bedrock. Over hundreds of thousands of years, this acidic water gradually dissolved the rock, creating larger and larger openings. Underground streams carved channels and chambers, following the path of least resistance through the bedrock, creating the cave system that existed when sea levels were lower. The stalactites that Cousteau discovered hanging in the depths of the Blue Hole represent different chapters in this cave's history. Analysis of their mineral composition reveals at least 4 distinct periods when the caves were dry, separated by periods when rising and falling, sea levels alternately flooded and drained the chambers. Each stalactite is a timeline written in stone, recording the slow drip of mineral-rich water over millennia when these chambers echoed with the sounds of air instead of water. Then came the Great Melting. As the last ice age ended and global temperatures rose, the massive ice sheets that had covered much of North America and Northern Europe began to retreat. Billions of tons of water, locked in ice for tens of thousands of years, returned to the oceans. Sea levels rose at a pace that was rapid by geological standards, though it would have seemed imperceptibly slow to any human observer. The rising waters first flooded the lower chambers of the cave system, then gradually filled the higher ones. As seawater invaded spaces that had been dry for millennia, the chemical balance that had supported the limestone cave structure began to change. The rock, already weakened by millions of years of water erosion, could not support the new stresses created by water pressure and changing mineral chemistry. The collapse, when it came, was probably sudden by geological standards, though it may have taken centuries to complete. Chamber after chamber gave way, their ceilings crashing down into the flooded spaces below. What had once been a complex 3-dimensional maze of underground passages became a single vertical shaft, a window into the Earth's interior that we now call the Great Blue Hole. In 2018, nearly 50 years after his grandfather's pioneering expedition, Fabien Cousteau returned to the Blue Hole with entrepreneur Richard Branson and a team of scientists equipped with the most advanced underwater technology available. Using sophisticated submarines and sonar mapping equipment, they were able to create the most detailed picture yet of what lies at the bottom of this underwater cathedral. Their discoveries revealed that the Blue Hole is still actively changing. At depths of over 400 feet, they found evidence of ongoing geological processes, areas where the limestone walls continue to erode, chambers that are still collapsing into deeper spaces, and most remarkably, a layer of hydrogen sulfide at the very bottom that creates a toxic environment where no life can survive. This chemical boundary, invisible to the eye but deadly to most forms of life, represents another timescale entirely, the deep chemical cycles of the Earth itself, processes that operate over millions of years and connect the Blue Hole to geological forces that shape entire continents. The hydrogen sulfide layer exists because at the very bottom of the blue hole, there is no oxygen and almost no water circulation. In this stagnant environment, bacteria that can survive without oxygen break down organic matter in ways that produce toxic gases. This creates a natural time capsule, preserving materials that fall into the hole in an environment so hostile that even the bacteria that normally decompose organic matter cannot survive. Spotted Lake, Canada. When the summer sun beats down on the sagebrush hills above Osoyoos, something ancient stirs in the waters of what the Silex people have always known as Kalilis Dibw. Each year, as the lake shrinks under the desert sun, it reveals a pattern that has been teaching the same lessons for thousands of years. 365 spots of crystallized minerals, each one a different color, each one containing medicine that flows from the earth itself. To the Silex Okanagan Nation, these spots were never just geological curiosities. They were gifts from the Creator, places where the earth offered its healing directly to those who knew how to listen. The elders tell stories that stretch back through generations about warriors who came here wounded in battle, soaking their injuries in waters rich with magnesium and sulfates that could heal both body and spirit. They speak of medicine gatherers who knew exactly which spots contained the minerals needed for specific ailments, knowledge passed down through careful observation over centuries. Each spot was mapped not just in space, but in time, the elders understanding that the lake's patterns shifted with the seasons, that different minerals concentrated in different areas as the water levels rose and fell with the rhythm of desert years. The Silex called it the Medicine Lake, a place so sacred that approaching it required purification ceremonies, prayers, and the proper protocols that honoured both the lake's power and the spirits that protected it. This was not simply a source of healing minerals, but a living entity, a teacher that showed how the earth concentrated its gifts in precise patterns, how patience and careful observation could reveal nature's pharmacy laid out in perfect geometric forms across the lake's shrinking surface. But in the 1960s, the lake that had served as a healing place for millennia became the property of Ernest Smith, a man who saw opportunity where the Silex saw sacred ground. Smith had plans that would have transformed Kalilis XW into a commercial spa, complete with hotels and facilities to extract and market the lake's mineral-rich waters to tourists seeking health treatments. To Smith, the lake represented untapped potential, a resource that could generate profit from the same healing properties that the Silex had stewarded for generations. The contrast could not have been more stark. Where the Silex approached the lake with ceremony and respect, taking only what was needed and always with gratitude, Smith's vision involved industrial extraction, permanent structures, and the transformation of a sacred site into a destination for paying customers. For nearly 40 years, the Silex watched as their Medicine Lake remained just beyond their reach, protected by property laws that recognized ownership but not sacredness, business plans but not spiritual relationships that stretched back to the beginning of memory. During those decades of separation, the lake continued its ancient rhythms, indifferent to the human conflicts that swirled around its shores. Every summer, as temperatures rose and rainfall became scarce, the water levels dropped and the mineral concentrations increased. Magnesium sulfate crystallized in brilliant white formations, sodium sulfate created yellow patches, and iron compounds added streaks of rust red to the lake's palette. The spots formed and reformed, following patterns that connected to underground mineral flows, seasonal temperature variations, and precipitation cycles that operated on timescales far longer than human legal disputes. Scientists who gained permission to study Smith's property discovered that the lake was more complex than anyone had realized. Dr. John Davidson, conducting one of the first systematic studies for the British Columbia Geological Survey in 1915, found that the lake contained not just the obvious sulfate minerals, but trace amounts of titanium, silver, and other elements that created an intricate chemical ecosystem. Each spot on the lake's surface represented a different concentration of minerals, a different balance of chemical processes, a different story about how water and time could transform simple elements into medicine. The lake's patterns, Davidson realized, were controlled by processes that operated across multiple timescales simultaneously. Daily temperature changes caused different minerals to precipitate at different rates. Seasonal weather patterns determined how much water evaporated and how concentrated the remaining minerals became. Longer climate cycles affected which underground springs fed the lake and how much mineral-rich groundwater reached the surface. And over geological time, the lake's position had shifted as the landscape itself changed, creating the current basin where minerals could concentrate in the extraordinary patterns that made each spot unique. But for all the scientific understanding that accumulated during the Smith family's ownership, the most important knowledge remained with the Silex people, who had never stopped watching the lake, never stopped teaching their children about its significance, never stopped hoping for the day when they could restore their relationship with KWW. Elders like the late Delphine Armstrong continued to share stories about the lake's healing powers, keeping alive the traditional knowledge that connected specific minerals to specific treatments, specific spots to specific ceremonies, specific times of year to specific kinds of medicine gathering. In 2001, after years of negotiation and fundraising, the Silex Nation accomplished what had seemed impossible. They purchased the land surrounding KWW from the Smith family, returning the sacred lake to the stewardship of the people who had always understood its true value. The purchase price of $720,000 Canadian was raised through a combination of federal government support, tribal resources, and donations from individuals who recognized the importance of protecting sacred sites from commercial development. The moment the Silex regained control of Klilika marked not just a legal victory, but a restoration of relationship between people and place that had been interrupted but never broken. Traditional protocols were immediately reinstated. The lake became protected from casual visitors, accessible only through guided tours that honoured both its scientific significance and its spiritual importance. Signs were erected in both English and Zilsen, the Silex language, explaining that this was a sacred place where traditional laws applied, where respect was required, where the ancient partnership between people and landscape could resume its natural course. Modern scientific research, conducted under Silex oversight, has revealed that the traditional knowledge about the lake's healing properties has a solid foundation in chemistry and biology. The minerals that concentrate in different spots do indeed have therapeutic properties that can treat skin conditions, joint pain, and other ailments. The timing of mineral collection that Silex tradition prescribed turns out to correspond with periods when specific compounds reach their highest concentrations. The protocols for approaching the lake, which required purification and prayer, served not just spiritual purposes but practical ones, ensuring that the lake's delicate mineral balance remained undisturbed. Today, Kliksi serves as a bridge between indigenous knowledge and contemporary science, a place where traditional ecological wisdom and modern research methods inform each other. Climate change has begun to alter the lake's patterns, with shifting precipitation and temperature regimes affecting how and when different minerals crystallize. The Silex are documenting these changes, combining their centuries of observation with new scientific techniques to understand how their medicine lake is responding to a changing world. Zhangjiajie stone pillars, China. The morning mist clings to the peaks like ancient breath, rising from valleys so deep that their floors disappear into white silence. From the glass elevator that carries you up through the cliff face, you watch 3,000 stone pillars emerge from the fog like sleeping giants awakening to greet the sun. Each pillar stands alone, impossibly slender, impossibly tall, some reaching nearly 1,000 feet into the sky, while measuring no more than 100 feet across their weathered crowns. They rise not in ranges or ridges, but as individuals, each one a solitary monument carved from living rock, each one balanced so precariously that it seems a strong wind might topple it into the valleys below. The silence here is profound, broken only by the whisper of wind through stone passages and the distant cry of birds that nest on ledges no human foot will ever reach. When the elevator stops and deposits you onto one of the viewing platforms that cling to the cliff faces, the full scope of this stone forest reveals itself in layers that seem to stretch beyond the horizon. Pillars near and far fade into blue haze, creating an illusion of infinite depth, as if you're looking not across a landscape but through geological time itself. Walk along the narrow pathways that connect peak to peak, suspended on bridges that span chasms hundreds of feet deep, and you begin to understand why filmmakers chose this place as inspiration for an alien world. The peaks around you seem to float in space, disconnected from any logical foundation, rising from mist-filled valleys that might as well be clouds. Each pillar wears a crown of green vegetation, creating the impression of gardens hanging in midair, ecosystems that exist in complete isolation from their neighbours, connected only by wind and the patient migration of seeds across impossible spaces. Today, tourists from around the world come here seeking the inspiration that created the floating Hallelujah Mountains in James Cameron's Avatar. They ride the world's highest outdoor elevator, walk across glass bridges that make them feel as if they're stepping through empty air, and take photographs that capture images so surreal they require explanation to be believed. But the stone pillars that surround them are telling a story that began long before humans existed, a story written in layers of rock that reaches back through hundreds of millions of years. Step back 24 hours to yesterday morning, when these same peaks emerged from yesterday's mist in exactly the same positions, wearing exactly the same crowns of forest, casting exactly the same shadows into exactly the same valleys. On the scale of human observation, nothing here ever changes. The pillars stand as solid and permanent as mountains have always seemed to human eyes, monuments to stability in a world of constant flux. But step back 24,000 years to the height of the last ice age, and the landscape around these pillars looked dramatically different. The climate was colder and drier, and the forests that now crown each peak were different communities of plants, species adapted to harsh conditions that no longer exist in this region. Ice did not cover these peaks directly, but the changed weather patterns carved different patterns of erosion, wore away different layers of rock, shaped the pillars in ways that were subtly but measurably different from what we see today. Step back 24 million years to the height of the Miocene epoch, and the pillars themselves were different. They were shorter then, broader, connected to each other by ridges and slopes that erosion had not yet carved away. The forests that covered them were unlike anything that exists on Earth today, communities of plants that evolved and disappeared long before the first human ancestors walked upright. Climate and weather patterns carved these peaks year by year, century by century, millennium by millennium, slowly separating what had once been continuous ridges into the isolated pillars we see today. Step back 200 million years to the Jurassic period, and the pillars did not exist at all. In their place lay a relatively flat landscape of sandstone layers, formed from ancient seafloors but now lifted high above any ocean. This was when the critical event occurred that would eventually create the stone forest. Massive tectonic forces associated with the formation of the Himalayan mountain system began to fracture and uplift the rock layers that would become Zhangjiajie. The Yanshan tectonic movement, as geologists call it, was part of the same immense collision between continental plates that pushed the Himalayas toward the sky. The forces were so vast that they fractured solid rock across hundreds of miles, creating the joint systems and fault patterns that would guide erosion for millions of years to come. The sandstone layers that had lain flat for eons were tilted, fractured, and uplifted, creating weaknesses in the rock that water and weather would eventually exploit. But even this moment of mountain-building violence was recent compared to the formation of the sandstone itself. Step back 400 million years to the Devonian period, when this part of China lay beneath a shallow tropical sea near the equator. The stone pillars that now pierce the clouds began their existence as sand grains on an ancient seafloor, accumulating grain by grain, layer by layer, over millions of years of geological time. The sand came from mountains that have long since been worn away to nothing, carried by rivers whose courses are forgotten, deposited in a sea that dried up before complex life colonized the land. Each grain was tumbled smooth by water and time, sorted by currents and tides, buried under subsequent layers until pressure and chemical changes cemented the individual grains into solid sandstone. The purest of these layers became quartzite, rock that is more than 90% pure quartz, among the hardest and most erosion-resistant materials on Earth. It is this extraordinary purity that explains why the Zhangjiajie pillars can stand so tall and slender without collapsing. Pure quartzite is stronger than concrete, more durable than steel, capable of supporting enormous weights without failure. While softer rock layers around them eroded away over millions of years, these pure sandstone layers remained, gradually being carved into the pillars we see today by the infinitely patient work of water, wind, and weather. The carving process continues even now, though at a pace so slow that human lifetimes register no change. Each rainstorm that sweeps across the peaks carries away microscopic particles of stone. Each freeze-thaw cycle opens tiny cracks a fraction wider. Each root that finds purchase in a crack gradually splits the rock as it grows. The pillars are not eternal monuments, but active participants in an ongoing conversation between stone and time, gradually changing their shapes in response to forces that operate on scales far beyond human perception. Modern research using cosmogenic nuclides, atomic particles created when cosmic rays strike the Earth's surface, has revealed that the current shape of the Zhangjiajie pillars began to emerge approximately 5 million years ago, when increased tectonic activity and climate changes accelerated the erosion processes that separated individual peaks from the surrounding landscape. This means that the stone forest as we see it today is relatively young by geological standards, a recent sculpture carved from much older stone. Yet even as erosion sculpts new details into each pillar, the fundamental structure remains controlled by the joint patterns and fault systems that were created 200 million years ago during the Yanshan orogeny. The spacing of the pillars, their heights, their orientations, all follow patterns that were established when tectonic forces first fractured these ancient seafloor sediments. Time operates here on multiple scales simultaneously. The daily rhythm of weather and erosion, the longer cycles of climate change, the geological pace of mountain building and continental drift, and the deep time of sedimentation and rock formation. Eternal Flame Falls, New York. Behind a curtain of falling water in a narrow gorge outside Buffalo, New York, something burns that shouldn't exist. The flame is small, no larger than a candle, flickering orange and blue in the constant mist of the 35-foot waterfall that shields it from the world. Visitors who make the muddy hike through Chestnut Ridge Park often stare at it in confusion, trying to understand how fire can survive in such a wet environment, how it can burn without any visible fuel source, and why it never seems to go out despite being constantly doused by spray from the cascade above. The flame dances in a small grotto carved into the rock face, seemingly fed by nothing more than empty space. There's no oil seeping from the stone, no obvious source of combustible material, no human-made apparatus keeping it alive. It simply burns year after year, season after season, in an impossibility made visible in the shadowy recess behind rushing water. Some visitors assume it's artificial, maintained by park services or fed by hidden gas lines. Others wonder if it might be some kind of chemical reaction, minerals in the rock creating combustion through processes they can't identify. For decades, this small flame remained a local curiosity, known mainly to hikers who discovered it by accident while exploring the network of trails that wind through the shale hills of western New York. Word spread slowly through hiking forums and regional travel guides, but the Eternal Flame Falls remained largely unknown to science, just another odd natural phenomenon in a landscape full of geological surprises. The first systematic scientific attention came in the early 2000s, when geologists at the State University of New York began investigating reports of natural gas seepage throughout the region. The fracking boom had heightened interest in understanding where and why hydrocarbons appeared at the Earth's surface, and the little flame behind the waterfall represented one of the most visible examples of natural gas emission in the entire northeastern United States. Dr. Arndt Schimmelmann, a geochemist at Indiana University, became intrigued by reports of the flame after hearing about it from colleagues studying similar phenomena in other parts of the world. In 2010, he began collecting gas samples from the grotto, using specialized equipment to capture and analyze the mixture of gases that was feeding the flame. What he found was far more complex than anyone had expected. The gas wasn't just methane, the simple hydrocarbon that feeds most natural gas flames. Instead, it was a complex mixture of hydrocarbons, including ethane, propane, and heavier compounds, that indicated a much more sophisticated source than the simple biological processes that create methane in wetlands and landfills. The chemical signature suggested what geologists call thermogenic gas, hydrocarbons created not by bacteria, but by the thermal breakdown of organic matter buried deep in the Earth's crust. This discovery led Schimmelmann to collaborate with Giuseppe Etiope, an Italian expert in natural gas seepage who had studied eternal flames around the world. Etiope had investigated similar phenomena in Azerbaijan, Italy, and other locations where geological processes bring deep hydrocarbons to the Earth's surface, but the Eternal Flame Falls presented unique characteristics that didn't match any of the standard models for natural gas seepage. Working together, Schimmelmann and Etiope published the first comprehensive scientific study of the site in 2013. Their research revealed that the flame was indeed fed by thermogenic natural gas, but gas that was seeping from rock formations much younger and shallower than the ancient deposits that typically produce such hydrocarbons. The gas was coming from Devonian Age shale layers, deposited roughly 400 million years ago when this part of North America lay beneath a tropical sea. The shale layers that feed the flame tell a story that reaches back to one of the most important periods in Earth's history. During the Devonian period, this region was covered by vast shallow seas teeming with marine life. As organisms died and sank to the seafloor, they were buried under successive layers of sediment in an environment with little oxygen. Instead of decomposing completely, the organic matter was preserved and gradually transformed by heat and pressure into the complex hydrocarbons that now seep upward through cracks in the rock. But the mystery deepened when the researchers analysed the isotopic composition of the gas. The carbon isotope ratios suggested that the organic matter that created these hydrocarbons had been subjected to higher temperatures than should have been possible at the relatively shallow depths where the shale layers now exist. This implied that either the shale had once been buried much deeper than previously thought, or that some other source of heat had driven the thermal maturation process. The answer came from studying the geological history of the entire region. The Appalachian Mountains, which extend through western New York, were formed by a series of tectonic collisions that folded and fractured the Earth's crust over hundreds of millions of years. During the most intense periods of mountain building, the shale layers that now lie relatively close to the surface were buried under miles of rock and subjected to temperatures and pressures that drove the chemical reactions needed to create thermogenic gas. Later erosive processes stripped away much of the overlying rock, bringing the gas-rich shale layers closer to the surface and creating the fracture systems that now allow the gas to escape. The flame at Eternal Flame Falls burns gas that was created during ancient mountain building episodes, trapped in rock for hundreds of millions of years, and only recently liberated by the ongoing processes of erosion and weathering that continue to shape the landscape. Modern research has revealed that the Eternal Flame Falls is part of a much larger system of natural gas seepage throughout the Appalachian region. Using advanced chemical analysis techniques, scientists have identified dozens of other seepage sites, most of them invisible to casual observation but detectable through sensitive instruments that can measure trace amounts of hydrocarbons in soil and groundwater. The discovery has implications that extend far beyond the small flame behind the waterfall. Natural gas seepage represents a significant but poorly understood component of the global carbon cycle, returning carbon that was removed from the atmosphere millions of years ago back to the modern climate system. Understanding where and why this seepage occurs is crucial for accurately modelling both natural greenhouse gas emissions and the potential environmental impacts of human activities like hydraulic fracturing. Recent studies using laser spectroscopy and satellite-based sensors have begun to map natural gas seepage across entire geological regions, revealing that the process is far more widespread than previously realised. The flame at Eternal Flame Falls, once considered a unique local curiosity, is now understood to be part of a global network of seepage sites where the deep carbon cycle intersects with surface processes. The ongoing research has also revealed that the flame itself plays an active role in the local ecosystem. The constant supply of methane and other hydrocarbons supports communities of specialized bacteria that can use these compounds as energy sources. These methanotrophic bacteria form the base of a unique food web that exists nowhere else in the region, creating a tiny oasis of biodiversity fed entirely by ancient carbon returning to the surface world. Waitomo Glowworm Caves, New Zealand. In the absolute darkness of the cave, your eyes search desperately for something to focus on, but there is nothing. The blackness is so complete that you cannot tell if your eyes are open or closed, so profound that it seems to press against your face like a physical presence. Then, slowly, as your pupils dilate fully and your vision adjusts to the absence of light, you begin to see them. Tiny pinpricks of blue-green light scattered across the cave ceiling above you. Dim at first, then growing brighter as your night vision awakens. One by one, they emerge from the darkness like stars appearing in the evening sky. First a dozen, then hundreds, then thousands of points of living light, each one no bigger than a match head but glowing with an intensity that seems impossible for something so small. They cluster in some areas like the Milky Way spread across a summer night, then scatter in others like distant galaxies separated by vast spaces of velvet black. The cave ceiling above you has become a mirror image of the night sky, a constellation map drawn not in distant suns, but in the bioluminescent bodies of creatures smaller than your fingernail. The silence here is as profound as the darkness was moments before. No wind disturbs these underground chambers, no birds call, no insects buzz in the traditional sense. The only sound is the gentle lapping of water against the sides of your small boat as it drifts slowly through the underground river that has carved these passages through 30 million years of patient work. Your guide's paddle moves silently through the black water, creating ripples that catch and reflect the constellation above, doubling the number of lights and creating the impression that you are floating through space itself. The air carries scents that exist nowhere else on Earth. The mineral smell of limestone dissolved and reformed over geological ages, the organic richness of bat guano and decaying plant matter, and something else, something alive and slightly sweet that comes from the glowworms themselves. Each breath brings this mixture of deep earth and living chemistry, a reminder that you are surrounded by an ecosystem that has been evolving in isolation for millions of years. As your boat passes beneath the densest concentrations of lights, you begin to make out details that were invisible when you first entered the cave. Each glowworm hangs suspended from the cave ceiling by an almost invisible thread of silk, like a living chandelier. From each tiny body, additional silk threads extend downward into the darkness below, creating what looks like a three-dimensional spider web, glowing with its own inner light. These are not decorations, but fishing lines, sticky traps designed to catch the small flying insects that occasionally venture into the cave's eternal night. The glowworms themselves are the larval stage of a fungus gnat called Arachnocampa luminosa, found nowhere else on Earth except in New Zealand and small parts of Australia. Each tiny larva has spent months in this darkness, slowly growing larger as it catches prey in its silk snares, its light organ producing a continuous blue-green glow through a chemical reaction that involves luciferin and luciferase, the same compounds that create light in fireflies and many marine organisms. But the light you're seeing serves a different purpose than the flashing signals of fireflies. These glowworms cannot turn their lights on and off. Instead, they glow continuously throughout their larval stage, which can last up to 11 months in the stable temperature and humidity of the cave environment. The light acts as a lure, attracting small flying insects that mistake the cave ceiling for a patch of night sky. When insects fly toward what they think are stars, they become entangled in the sticky silk threads and provide the glowworms with the protein they need to continue growing. The cave system that houses this extraordinary light show was born in an ancient sea that covered this part of New Zealand 30 million years ago, during the Oligocene epoch. The limestone that forms these caverns began as countless marine organisms living and dying in warm, shallow waters, corals, shellfish, microscopic foraminifera, and other creatures whose calcium carbonate skeletons accumulated on the seafloor in layers that eventually compressed into solid rock. When tectonic forces later lifted this limestone above sea level, slightly acidic groundwater began the slow process of dissolution that creates all limestone caves. Carbon dioxide from the atmosphere and from decaying organic matter dissolved into rainwater, creating a weak carbonic acid that could slowly eat away at the limestone. Drop by drop, year by year, century by century, this acidic water carved passages through the rock, following fractures and weaknesses to create the three-dimensional maze of chambers and tunnels that exists today. The underground river that carries your boat is part of this ongoing process. The water that flows past you fell as rain on the hills above days or weeks ago, percolated down through soil and rock, and emerged in these caves as part of a hydrological system that connects the surface world to these hidden depths. The river continues to carve and modify the cave system, widening passages, creating new chambers, and occasionally causing collapses that reshape the underground landscape. Modern research has revealed that the glowworm populations in Waitomo represent an evolutionary experiment that has been running for millions of years. When these caves first formed, and the ancestors of today's glowworms first colonized them, they entered an environment utterly unlike the surface world they had left behind. In the cave's constant temperature, stable humidity, and complete darkness, different survival strategies became successful than those that work in the variable, light-filled environment above ground. The continuous glow that makes the glowworm so spectacular to human visitors is actually an energy-expensive survival strategy that only works in an environment where food is scarce and competition is limited. Each glowworm must produce light continuously for months, burning through chemical energy reserves while waiting for the occasional insect to fly within range of its silk snares. It's a patient, long-term approach to survival that reflects the cave's own geological patience, the slow accumulation of small advantages over vast spans of time. The blue-green colour of the glowworm's light is no accident. This wavelength penetrates the cave's darkness most effectively and is most visible to the flying insects that serve as prey. Over millions of years, natural selection has fine-tuned both the intensity and the colour of the light to maximise its effectiveness as a lure while minimising the energy cost of production. Recent studies using DNA analysis have shown that the Waitomo glowworm populations have been genetically isolated from their surface relatives for so long that they have begun to evolve into distinct subspecies. The cave environment has selected for individuals that can survive longer without food, that produce more efficient light, and that can navigate the three-dimensional space of the cave system more effectively. Each generation represents another step in the slow process of becoming a truly cave-adapted species.